Hello and very good evening and a warm welcome to today's live session. In the early 1900s, the halls of Gottingen University, a quiet revolution began. Not with a telescope or a particle accelerator, but with the mind of one extraordinary woman, Emmy Noether. In a time when women were not even allowed to teach officially, she lectured under David Hilbert's name. Yet her ideas soon shook the foundations of physics itself. She revealed a profound truth that every conservation of laws of nature is born with a symmetry. Energy conservation, a reflection of symmetry in time, momentum conservation, symmetry in space, and so on. Noether showed that the universe does not just obey equations, it follows patterns of deep harmony. She gave physics a hidden grammar, the logic beneath every law that we know. And today, as we continue that search for harmony from Einstein's curved space-time to the enigma of dark energy, we are joined by someone who explores those frontiers. Dr. Akshay Rana, Assistant Professor of Physics at St.Stephen's College, University of Delhi, is a cosmologist and a theoretical physicist whose research tests the limits of general relativity and studies how the universe's fundamental constants might evolve. He is also the co-author of the Indian adaptation of Willis' Introduction to Special Relativity and a passionate science communicator dedicated to make complex ideas seemingly beautiful and clear. So to all our viewers, welcome to Physics for Students, where we unravel the elegant ideas that shape our understanding of the cosmos. In today's episode, we dive in Noether's theorem and the symmetry of the universe, a story where mathematics, physics, and beauty meet. Without further ado, let me give a warm welcome to Dr. Rana. Dr. Rana, welcome to the show, and it is a pleasure to have you with us.
Hello, Doctor. Hello, everyone, and good evening to all. So, Dr. Swana, can I show my presentation right now?
Absolutely. So I will just set what we are going to do is that Dr. Rana is going to start with a presentation. This is going to be all that we will discuss. I'm thankful that he has taken entire day making this presentation simple, and I'm sure the viewers going to enjoy. Requesting the viewers that if you have any question, you can ask in between, but it is better that if you can keep your question and we ask at the end, because this is going to be a very important and a wonderful presentation. Dr. Rana, over to you. I will just mute myself. You can go ahead and start. And if I have a question or something, I will jump in between. Over to you, Dr. Rana.
Okay. Yeah, so good evening, everyone. And first of all, I want to give my thanks to Dr. Sonak for giving me this opportunity to come here and to talk about this interesting idea. And first of all, it's important to highlight the contribution of Dr. Shonak as well, which I'll do in the beginning. I have gone through his channel, and the kind of content he's providing for the theoretical physics is really a service to the physics, or especially to theoretical physics. So many kudos to you, sir. Today, I am going to talk about a very fascinating idea, and somehow, if we believe that the physics is the study of the nature, then I would say that this word symmetry is lying behind that particular physics. And in some sense, whatever we are going to talk about today, it's going to be applied to the whole universe. So the application of this particular word symmetry is not going to be limited to one particular field, but everything all around us is going to be controlled or going to be directed by this word called symmetry here. So just to begin with, I want to ask a few questions. And these are the questions not which even the physicist might have thought about. Even in general life, anyone might have thought about in the old times as well. That every day when we look around the sky, we see that the sun rises in the east and then it falls or it sets down in the west. Similarly, we do see the motion of the moon all around us. And if we do have a pendulum, then continuously if we oscillate it, we figure out that every time if there is no damping in it, it is going to follow a certain motion, means it's going to be cycling in nature. And that motion, in the absence of any sort of external perturbation, it's going to keep following that particular motion. Apart from that, if we'll see, there are going to be the generation of many symmetric objects all around the universe, all around the nature. So in some sense, it's very easy for us to figure out that our universe or the nature, when it designs something, when it either create a equation or either it create a object or howsoever the mechanism it follow, it do prefer to have some sort of similarity or some sort of symmetry in those objects. And from the very beginning of the understanding of the universe or understanding of the physics, the curiosity that humans used to have, they start noticing these patterns, and noticing those patterns, and then further to evolve about those patterns, how those patterns are going to lead to the some sort of physical explanation. I'll say that's the whole emergence of the physics, the way physics emerged over the time. So in the sense, a general person will be asking the questions like I have given you, but if I'll go to the way a physicist will ask, instead of asking a question like why the sun moves in a certain way, why the pendulum do oscillate in certain way, they will ask questions in more physical way, which are going to have certain words, which are going to have certain physical relevance as well. Like the asking a question like why do we have energy conserved in the universe, means we don't do hear this statement that energy cannot be created or it cannot be lost, it's the conserved overall. Why is it so? Similarly, for the momentum, we do talk about the principle of conservation of momentum or angular momentum, but how do we know about it? What is the origin of it? Similarly, if you have a ball, let's say if I'll have a ball here and if I'll try to throw it up, either I am going to throw it on a vertical motion here in Delhi or you in Kolkata or anywhere in the world, if I consider the gravity is going to be uniform, then everywhere it's going to follow the same equation, same law of motions. The law like F equal to ma, our gravitational law, our Coulomb's law, all these laws are valid universally. What is so special about this nature? How can nature make something to be universal? What is the mechanism of the nature through which it can force the all these laws, all these particular objects to follow in a certain manner? And that's the question that kind of very intriguing in the manner, and that should kind of bring a lot of curiosity to any physicist or to a general audience as well. Now, if I'll go to the word, the answer means, just instead of keeping any mystery or to any suspense to it, the key word, if I'll go about it, if I'll just talk about the any connection that this particular formulas or these particular patterns that we do observe in the universe, those do have one simple answer. The one simple solution to their query is that is the word called symmetry. Now, if I haven't talked about the symmetry, I'll be explaining it to you in detail. But if I'll go by the verbatim definition of the dictionary, then the word symmetry means something which is going to be balanced. Mostly it's about the geometry of the object. It's about if something is similar in the size, position, shape or something, then we call this object is geometrically symmetric. Like when we do talk about human body, we can say that our human body is having bilateral symmetry perpendicular to across the perpendicular axis. Now, means our heart is slightly on the left side, but kind of it's the bilateral symmetry. And the answer to this whole stuff is given by one lady, as Dr. Sonak has already talked about, by the Emmy Noether. So this symmetry was obviously there; they were present throughout the time, but the main answer was given by the Noether, and the understanding how do we develop this relation between the forces and these fundamental laws, and how do we relate these patterns that we observe with universe with these conservational principles. That particular answer is given by the Emmy Noether. So my talk is going to be in two ways now, because this talk is all about Noether and Noether's theorem. So I'll briefly talk about the Emmy Noether, how was his journey, what kind of struggles he had in her career, and then I'll go to the second topic, which is going to be about the symmetry, and then we'll dive into the whole mathematical development of the theory. So let's try to see what all Emmy Noether have done had done in her career. So Emmy Noether was the daughter of a prominent German physicist named Max Noether. And because his father was the mathematician, her education, basic education, was also very detailed and very prominently in the mathematics only. But she faced one struggle when, after completing her basic education, when she went to the university. At that time, in the Germany, women were not allowed to go to the university. Means they were allowed to go to the university, but they were not allowed to get the admission. Were not allowed to be on roll. So after completing her basic education, she start going to the nearby university in the same place. She was from the a place called Erlangen, from the Germany only. So she started going to that university. She attended all the lectures over there, but over the time, she was not able to sit for the exams. She was not allowed to give the exams to get enrolled in any course. But luckily, over the time, in 1904, Germany and especially the University of Erlangen changed that particular rule. They allowed the women to get on roll, and that's how first time Emmy Noether get a admission on an official role in the University of Erlangen, and immediately she joined the doctorate program. She started working with a very prominent mathematician named the Paul Gordon in the University of Erlangen, and which is also known as the king of invariant theory. And with that, her PhD career, her career in the field of mathematics evolved. But after completing her PhD in 1907, she faced another challenge. The challenge was, though the girls or women were allowed to sit for the exams to get on roll, but they were not supposed to be the professor. They were not allowed to get a job in the university. And this another hurdle, though she was very curious to work in the field of research, to work in the field of invariant algebra, but she was not allowed to get on roll as a professor or assistant professor or any other post in the university. So then she started teaching in the University of Erlangen on a research or unofficial lecture kind of post. She used to get mere salary for giving lectures, but no recognition, no. And this is somehow irony in the nature. I mean, she was allowed to teach. It's not like women were not allowed to teach. She was allowed to teach, but again, she was not allowed to be known as a professor, even though she was a very kind of a favorite professor of the students that she had at that place. But eventually, she kept working on the same post without any recognition. For 7-8 years, she taught in the University of Erlangen. And over there, she was working continuously in the field of invariant algebra. Her work was so prominent that she became famous and get recognition all across the Germany and all across the world in that sense. And to her, I'll say to her surprise, or in some sense of for all the hard work that she had put in her work. In 1915, when Einstein was developing his theory, or the general theory of relativity, at the same time, they were in the a place in the university which is known the University of Gottingen. At that particular time, this was the kind of a hub of the mathematics or the science. All the prominent scientists were sitting in the Gottingen University, and this was known as the famous Gottingen Circle as well, where the Albert Einstein, David Hilbert, Felix Klein, all these were sitting there working on their respective subjects. And as we know that the Einstein developed the whole theoretical framework of the general theory of relativity, but the whole tensor and the Riemannian theory was given based on the work done by the David Hilbert. So both of them.
Sorry to interfere. This is so interesting. I will just plug in one small information that when Hilbert and Klein actually, what Sir is telling Dr. Rana is that when Hilbert and Klein actually realized that Noether has an exceptional work in terms of invariant theory of abstract algebra, they actually called Emmy Noether to Gottingen. And some of the professors, they protested that how can all the Germans can learn from a woman, because a woman cannot become a member of the faculty. The same thing what Dr. Rana told. And it was during that time that David Hilbert made a very interesting and a famous quotation or remark, I would say. He told that I do not see that the sex of the candidate is an argument against her admission as a lecturer. After all, we are a university, not a bathing house.
That's great. Yeah, that's to the point, sir. So absolutely. That's what I was trying to highlight. That at the means, though you have completed the statement. So It is in 1915 or in the same year when the Einstein gives the general theory of relativity. They faced certain issue, and now that issue I'll be talking about. The issue was also very interesting. They were talking about because Einstein general theory of relativity, when he sold it for the universe or for something called the FLRW metric, which I'll be talking about later in the talk. They figured out that when they try to ask a question whether the energy of the universe, because we consider our universe to be expanding universe, and it's not going to have any boundaries. It's completely homogeneous and isotropic in that particular sense. So they were finding it difficult to absorb that can we find out some single number for the total energy of the universe, because by nature we do have this sense like for any system that energy need to be conserved. So they were having this intuition that the energy for the universe should also be conserved. The total energy for the universe would be a finite number. And both Einstein was very strong, having inclination towards this idea. Even Hilbert was mathematically trying to figure out some way, and to get rid or to get the better understanding of this issue, they called Emmy Noether. And Emmy Noether came, and within I think 3 months he was able to give the complete version. Otherwise, till that point, Einstein and Hilbert both were thinking about that there is something wrong with their theory, general theory of relativity, and they were trying to figure out what is wrong about it. Why this theory is not giving some global number for the total energy of the universe. So they were trying to figure out, but neither proved it. What I'll be talking later in the talk, and that's how the problem get resolved. So the work that she did was later get published in a German peer-reviewed journal. Its English version is available here. One can note down this archive number. One can go and read the same work. It's very detailed version. You can find out a lot of reviews as well. Maybe Dr. Shonak might share some books as well. There are many books written about the Noether and Noether symmetry, and a lot many, which I thought I might refer later, but maybe Dr. Shonak can also share that work. So now, when we have talked about the Emmy Noether, now we can see the kind of contributions he had, and the whole idea about the symmetry came. The development, the relation between the symmetry and conservation principle comes from there. But these symmetries were not new. They were always there, and all the laws of physics before the general theory of relativity in the whole 19th century. We were talking about thermodynamics, we were talking about electromagnetic theory. Before that, we were talking about the whole gravitational laws, optics, all these things we were talking about in the 17th, 18th, and 19th century. So when we talk about modern physics, that we do talk about STR, GTR, and the quantum field theory that came in the 20th century in that sense. So anyway, the symmetries were available, or different kind of these patterns were already visible in those subjects as well, like which the physics that we have understood till the end or till the beginning of the 20th century. So we'll try to gauge some idea what kind of symmetries and what does this word mean. First thing that I want to talk about is that what do a physicist understand from the word symmetry? As I have told about the dictionary, for a person, if I'll just use the word symmetry in daily language, it will be something related to pattern, some similarity or something. But as a physicist, we do have a slightly different, or I'll say quite different idea of the word symmetry. So let's try to explore what does this word symmetry mean for us. So now, when I'm saying that some similarity I'm seeing on the basis of just on the basis of the way a object, I'm going to make some change in object, that's the geometrical symmetries. Like I'm just talking about the geometrical shape, how the object is going to move and everything. Apart from that, we interestingly see certain thing, that we have physics laws, we have equations of motion, we have solutions to the equations. And those solutions, sometimes when we try to make change in certain parameters, those solution remains invariant. The word invariant means, again, very much analogous towards symmetry. Means if you have an equation, you make certain changes and the object remains the same, or certain feature of that particular object remains the same, then we figure out the change and the quantity to which we have made the change. Okay, so there are two things. One, what is the change, what is the transformation that we are trying to make, and to what object we are making a transformation. So for a physicist, because we have to deal in the terms of mathematics, we have to talk about the mathematical equation. So we have if as a physicist, if I am going to talk about like this pendulum, let's say if I am going to have this pendulum, this consider it to be a pendulum. Sorry, it's not though, but if it is moving, what I'll do, I'm going to write down in a mechanics way, I'm going to make a free body diagram of it. I'm going to write down all the force equations and then figure out equation of motion. And that in that equation of motion, it's going to be based on certain parameters. It could be based on parameter, like there's going to be position parameter, there is going to be time parameter in it. And if I make certain change in these parameter, either in x or either in the t, and then try to figure out if I'll make change in x, and even then the equation is going to remain same, or the motion of this particular object is going to be the same, or any other feature, we will figure out if any other feature of this object is going to be remain same, then both these things become very interesting for us. We this particular action that we have taken, the change that we have made to the system, and even to the equation that we have, we are trying to make any change. So what I want to emphasize with this, whenever as a physicist I want to study the word called symmetry, then first thing I'm going to apply it on some mathematical system, obviously some equation or that operation that I'm going to make, that's also going to be some sort of mathematical in the sense. So for 3 questions which I would like anyone to think about, and during this talk as well, whenever I'm going to talk about any symmetry, one should think in their mind like what these 3 questions one should have in their mind. First thing, any change that I'll be making, what is that change? Whether the change I'm making a change in the time, whether I'm making a change in the position, whether I'm making a rotation to a object, so rotation is also a change. I'm putting a particular object before a mirror, that could be mirror reflection. There can be change if I am talking about, let's say, quantum mechanics. I am a wave function, then I can change the phase of the wave function. Or if I'm talking about classical dynamics or quantum field theory, then there are going to be fields if I'm making a change in the field. So depending on the subject, depending on the mathematical development of a particular topic, there are going to be quantities on which I can make the change. So we need to be very clear whenever I'm going to talk about that, what is the quantity that we are changing. So that's the first important thing. There's going to be different quantity which we'll talk about. Second thing, we need to ask, to what equation are we making these changes? Those equation could be any physical law, means like it could be F equal to ma. That's our simple equation, or second law of Newton's law of motion. Then we can have, if you are talking about classical dynamics, we write down the Lagrangian or something called action, which I'll talk about. I'll just try to give you a refresher on that as well. We can make changes on that. We can see that if we try to make certain changes in a particular system, the whole system, even if we are making change, the energy is not changing, momentum is not changing. So all these are going to be the different kind of transformation quantities in which we are going to make the transformation. These are 2 things. Third thing that is going to be, if I'm making certain change in the system, but the particular quantity or particular mathematical thing is not changing at all, what does it mean physically? And the whole Noether's theorem and the whole understanding is lying in that particular, how do we make a physical sense of it? Okay, so that's what we are going to figure out. So keep these 3 questions in mind. When I'll be going, it might be overwhelming right now, but I'm going to break down everything. And whenever I'm going to talk about a particular symmetry, you can think about these 3 questions. Okay. So
Sir, I have a small question, whatever
Yes,
the way you are explaining beautifully. In a deeper sense, this symmetry, does it actually also refer to the principle of least action, how the motion or the Lagrangian is taken? Is it somehow related to that also?
Okay, so it is. I think I'll be when I'll be talking about the continuous symmetries, I'll come to that point. I'll be talking about the thing, because right now I think I'll need to talk a little bit about
I
what
got
that
your
is
point.
mean.
No problem. No problem.
So
Okay.
I'll be okay. Just in a while, you get the idea.
Yeah. Thank you.
So now, first thing that we do see, I want to talk about that. What are the different kind of symmetries? Generally, when we do talk about symmetries, we classify the symmetries in 2 ways. One, we call the continuous symmetries, and another we call the discrete symmetries. Just try to understand the difference between 2. I'm going to give a very geometrical way of understanding it. If you can see this piece of paper. Now, for me, this is a state of this particular paper. This is a particular geometrical form. Now, when I'm saying I'm going to make certain change, so this is the system. the first question, the second question, I'm going to make certain change to it. And what change I'm going to make? I want to rotate it. If I'll rotate this piece of paper, this is a square. I have planned to make it a square. If I'll rotate it, it is going to be same if I'm going to rotate it by 90 degree. If I'll make another rotation by 90 degree more and make another rotation by 90 degree more, so every 90 degree rotation is going to give me the same position if I consider it to be completely uniform. Similarly, if I'm going to have, I'll try to see, let's say it's equilateral triangle. If I'm going to say that it's equilateral triangle, if I'm going to rotate it by 120 degree, this is going to be the same form. If I'm going to rotate it by another 120 degree, it's going to be the same form. So means when there are going to be geometrical objects, when I'm going to make change, but that change is going to be discrete in nature. Means for a rectangle, if for a square, it's going to be 90 degree. If I'm going to talk about a rectangle, then I have to make that rotation of 180 degree. So whenever those rotation or the change that I'm making, those changes are going to be discrete in nature. Then we classify all those objects in the symmetries. Symmetry means the geometrical feature, geometrical orientation, or the way this object do look, that is going to be the same. If I'm going to make a rotation of 45 degree, this will be something like this, which is very much different. It is not going to be symmetrical, or it's not going to be symmetrically the same object that we begin with. So all these kind of object where our changes are going to be discrete in nature, we are going to classify them as the discrete symmetries. While think about either this disk. Consider that this particular sides are completely plain, or no structure is there. If I'm going to make a slight rotation for this, so in this particular case, if I make a rotation of 1 degree, 2 degree, 10 degree, 100 degree, or 0.1 degree, or any angle I do choose, if I'm going to make rotation, every time this particular disk will look same. If I'm going to have this ball, let's say, if I'm going to rotate it by in the r, if I'm going to write down it in the spherical coordinates, if I'm going to rotate, make any sort of rotation or to it, then every rotation, every change, whether it's very large change or very small change, the geometrical structure of this object is going to remain the same. So it means there are going to be certain class of symmetries or certain objects where the transformation need to be discrete in nature, and there are going to be certain transformation which are going to be continuous in nature. So on the basis of that, we define these symmetries in the two parts, either discrete or in the continuous. So I'll be talking about different kind of discrete symmetries, but one symmetry that I have told about, this is the rotation. So n-fold rotation, here I am using a word called n-fold rotation. It means for this square, this is going to be 4-fold rotation. For a triangle, it's going to be 3-fold rotation, because I can make 3 rotation similarly and I'll come to the same object. For a rectangle, it's going to be 2-fold rotation. And while in the case of the continuous symmetry, any angle continuously will change, the object will remain same. So you cannot, that's going to be an infinite number of choices that you can have in that particular continuous symmetry. And over there are going to be objects what the quantities in the case of continuous symmetry will change the time, will change the space, will change the rotation and phases. So let's try to dive into the whole flow of the talk is going to be. Firstly, I'm going to spend some time to talk about the discrete symmetries only, and then I'll go to the continuous symmetry. I'll just try to, and it's during the preparation of the talk, I'll also get to know a lot many new things as well. It was so fascinating to see that just in the discrete symmetry, the kind of beauty these particular symmetries do have. I'll hope all of you will also appreciate in a while. So
absolutely, sir. We already got a comment from somebody called Raina Singh, and she's telling very interesting.
Okay, so now one challenge as a physicist we do have is that when we do talk about all these symmetries, we are not going to talk about each and every symmetry, every rotation in a particular or singular manner. We have this particular tendency to get a abstract understanding. We want to make a abstract formulation for the understanding of the symmetries. So the language that we use for understanding or developing the abstract idea about the symmetries, we use a mathematical quantity, and that particular quantity mathematically that we call it a group theory. That's a complete subject in itself. I'll just briefly try to give you an idea wherever it's needed. But so in some sense, group theory is the language of symmetry for me. Means you cannot understand the symmetries without having an understanding of groups. Groups are nothing but set of certain elements which do act in a particular manner when you try to apply some operation. Means, let's say you have a set of real numbers, then you have a operation like addition or multiplication, and it should supposed to follow certain rules. So I am just going to give you, those of you might have done any course on group theory, they might can understand it very easily, but I'm just going to use some basic terms which are going to be very relevant, because these are going to be very important for us to develop further, because that's the basic language of symmetry. So a group is nothing but a set which do follow certain properties or certain conditions under certain operation. So here operation could be anything, positive, negative, or anything, or there can be set could be having any elements, and it's supposed to have few properties which we call the closure property. Closure property means if two elements A and B are going to be the part of a set, then if you'll apply the same operation A plus B, let's say in the case of real set or integer set over the positive plus operation or positive operation, then it's going to be A plus B also going to be the element of G. Similarly, there is going to be identity, means there is always going to be an element which you will apply on certain set, and there is not going to be any change in the system. Corresponding to every operation that you will apply, you should be having an element in the same set which can kind of reverse the whole effect of that particular operation. Then you call it something called inverse object. There is a property called the associativity, which says that if you have the bracket in the operation, that the whole impact of the bracket is not going to change anything. So if a particular set of operations do follow these 3-4 properties or 4 properties to be particular, we call it kind of group. I'll try to give you the examples, and there are some specific kind of groups which I might use these words, something called abelian group. The abelian group is nothing but if there are two operations A and B and two objects A and B, if they are commutative to each other, means A dot B or B dot A, if both are similar in the case, we say that the particular set or the particular group is the abelian group. You can understand in the manner like when you have two matrices, the matrix multiplication of two objects, that's not commutative. A matrix multiplication B, if A and B are two matrices, is not going to be equal to B matrix multiplication A. So in that sense, matrix multiplication is not commutative, but in general, any integer multiplication, that's commutative to each other. So we can call that set to be abelian in nature. Then we do have something called cyclic group as well, which in case I'll talk about it. Okay. So let me just give you the examples, few examples of the set. If you have, I am writing down these certain groups. These groups are under certain operations. So let me just talk about this particular set. I am talking about the third one, Z3, if you can see in the screen. This is a set of rotation of equilateral triangle, which is going to have a threefold symmetry. So means if I'll consider this is going to be the first orientation of this particular triangular. If I'm going to make it rotate by 120 degree, then this is going to be the second element. If I'm going to, the operation which is going to apply, that's going to be the second element of the set. If I'm going to rotate it further, it will going to be the third element. And after 3 operations like this, again, I'll be into the first state wherever I was in the beginning. So means if I want to rotate, if I want to see how many different operations I can have in a set of a rotation of triangle, equilateral triangle, then I'm going to have 3 elements in it. So I'll call it a threefold symmetry, and this set is going to follow certain properties of which I have talked about in the previous slide. Similarly, if I'll talk about a square, it's going to have a 4-fold symmetries, which you can figure out. R naught, there is going to be 90 degree, 180 degree, 270 degree, and then it's going to be the same. Similarly, they are going to be, if you talk about the 3D reflection along the YZ plane, like you just make a reflection in the coordinate plane. Let's say you have XYZ, you just make a reflection, mirror reflection, in then the coordinates will be going to be minus X, Y, and Z. So it's just a reflection, and if you just again figure out the reflection, it will be the same object. So it's a two-fold symmetry. So there are going to be only two elements in this set. One, this is the one image, and another is going to be its reflection. So it's going to be only two elements in that. So all these are going to be the set of V, and they are going to be finite in nature. Obviously, because this is a discrete set, they are going to be finite in nature, and all these can be generated by this one same element. So that's why we call it them the cyclic groups. Those of you must have studied group theory a little bit, they must be knowing it. So it's the very basic of the group theory. Similarly, we also define another class. Let's say when you make these rotations, if you club them with the reflection as well, then again, when you have, means that's a very interesting thing. If you have one kind of symmetry in a particular object, and if you'll combine and then you apply the another symmetry on it, then the combination of these two symmetry will give birth to another symmetry. So that's very interesting. So now it's very much like when you are having this rotational symmetry on this particular rectangle that I'm talking about, and along with that, along with every rotation, if you are going to have a reflection as well. So means after every rotation you are having a reflection. So in that way, rotation and reflection can club together. They can also give you all sort of different new symmetries in that particular object, where the object will look same. So whenever you combine this rotation plus reflection kind of symmetries and again form a large set, we call those set by a name called something called dihedral groups. So this is the few names which we'll figure out. So few things which we have learned, that discrete symmetries, we are not going to talk about individual symmetries. We are going to talk in the terms of groups. And all these groups for the discrete set are going to be finite groups. That's the key point one should keep in mind. Okay. Now, that way we can have, and all these symmetries, you must be saying that I started with a statement, oh, all the symmetries that we do see or generally perceive in nature are very geometrical nature, where we talk about the structure and figures. Now, but at a physicist, these are not the only thing which interest us. We just try to dive into the mathematical equations, and which can show us, we try to figure out deep down in the mathematical equation and try to understand where, what different kind of symmetries can be there. And obviously, instead of looking just on the geometrical structure of the objects or this particular rectangle, triangle, we'll look into the equations now, and we'll try to see what kind of symmetries they might be having. And I'm going to talk about 2-3 extremely important discrete symmetries. There can be many more symmetries, but I'm going to talk about these 3 important symmetries which are very fundamental to the nature. Let's talk about this particular symmetry, which we call something called charge conjugation symmetry. Charge conjugation symmetry, just I am hoping that the students here, if they are the student of the graduation first years, they must be knowing about at least the Maxwell equation, at least.
Absolutely. So, that is assumed, and you can go ahead. Yeah. That is
so
quite true.
Now whenever we try to develop any system, if we think about our theories, let's say if I'm going to develop the electromagnetic theory, then obviously there is going to be charged particles. Then we do talk about quantum mechanics. Then again, we talk about different kind of charge or the probability associated to the system in the quantum mechanics. So eventually this charge conjugates, and obviously we write down certain equations, we find out solution for that particular system. Let's say for a charge moving in electromagnetic electrodynamical system, it's supposed to follow the Maxwell equation. And if we can always write down the Maxwell equations for a electron, let's say, or a charge density or positive charge density. If I can make a change in my equation, and the change is, if I'll replace my particle, let's say there is an electron which is going to have positive charge. If I'll replace it with something called the negative charge, if I'll replace it with the positron, if I make this particular change and then try to apply this change on my equation, or the equation for the case of electromagnetic theory, I'm going to talk about the change in the Maxwell equations. So it's very easy to do. One can just try to figure out. Here you can notice on the left hand side, if I can, my cursor, is it visible? My cursor, sir?
Yeah, visible.
So
Sir, may I interpret? There is one quick question coming up from somebody called Pavanil. He's asking that what would we say about circle? How many folds symmetry it is?
okay, so yes, for circle, as I pointed out, there can be infinite folds, so it's not going to be a finite set. Yeah, it's not going to be finite. It's not going to have a finite number of symmetries. It's have infinite number of elements, and for that we will call this symmetry to be continuous symmetry, which I'll be talking about in a while after
Okay,
completing. So
fine.
this symmetry in this one is the continuous symmetry. Continuous means if you can make a delta x change or delta theta change in the angle, very small, minute, infinitesimal change, even then the system is going to remain the same. So no changes
Okay.
you will be able to identify by making any finite
Okay.
angle in that
Right.
sense.
Thank you, sir. And I'm going back to the presentation. Yeah.
Fine. So I'm going to leave you with slight some mathematical calculation as well, which you can try to verify. So I'm just claiming this. So when you are going to make the change in the electric field, then you'll figure out the quantities like the charge density, then the current density, electric field, magnetic field, all these will change. And if you'll put all these things in your Maxwell equation and try to rewrite for your equations, means either you write down your your Maxwell equation for electron or you write down it for the positron. In both the cases, the equation will not change. Means changing the charge is not changing anything for you in the terms of Maxwell equation. So the parameter, again, remember those two questions which I asked. What we are changing charge, and in what we are changing, we are making change in the Maxwell equation in case we are talking about in the case. Quantum mechanics, I can talk about the pair production where you have electron positron coming together and creating the photons. Over there, if you'll make the change, electron will go to positron, positron will go to electron, system will remain same. The equation are not going to, it's also charge invariant. Then if you have electric field, you change E to minus E, then for positron, it's also going to be the same. Generation of electric field is going to be same. So means there are going to be lot many theories when you develop. So I can conclude with this that for the electric field, okay, I think I'll just give me 1 second. I'll
Yeah, just requesting the viewers to wait kindly. Okay. Abhig Hazra is telling getting
sorry,
interesting.
switch on.
No, that's fine. Abhig Hazra is telling that it is getting interesting. So thank you, Abhig, and willing to stay online. Yes, sir. Please continue.
So now, means one thing that I can say, means I'm not diving deep into every topic here. I'm not proving it. I'm leaving it for you to figure out. I'm just making these claim per se for you. But I just want to highlight here that for the based on this, I can say electromagnetic theory is going to be charge invariant. Means if you are going to make this symmetric transformation of charge, it's going to be invariant. Even quantum mechanics is going to be for that case. But there is one very interesting feature, that's the beta decay, and most of you must have studied that the beta decay does not follow this charge conjugate symmetry, and it do violate it. So now beta decay means there are different kind of beta plus beta minus. I'm not talking about all different kind of beta decays here. If I'll just go by the basic understanding that a neutron will go into a positron, then obviously there is going to be one electron for the charge conservation, and along with that for the energy maintenance there is going to be this anti-neutrino which will be coming out, which the whole theory is being developed. But when you try to observe this particular equation and you will try to make a charge transfer, so electron is chargeless, proton you are going to, means electron and proton are going to be, the changes can be in two manner. Either you keep your neutrino and the neutron and the proton same, and then you make the charge change in the electron will go into the positron, but then your anti-neutrino is not chargeless. So in that particular case, if there is going to be that kind of transformation, then charge conservation will not hold. Means charge conservation means because proton and electron both have the +1 and -1 charge, so that's why the whole equation get neutralized. If I'm going to just make electron to be positron, the equation there is going to be net charge on the left hand side. So eventually then could be I'll instead of proton, if I'll talk about anti-proton, that might seem like a physically valid condition. But I'll just try to explain. I try to give the analogy. Why then, if this is possible, why I'm saying that the charge conjugation symmetry is not going to hold, or it's going to get violated in the weak interaction? weak interactions are very interesting in nature. So when we do have any object in the weak interaction, so we associate, let's say if I'm just going to talk about neutrino or any other, let's say I'm going to talk about any neutrino or anti-neutrino, along with the charge and along with the spin, we associate one more property to this particular object, and that we call the either we call it the handedness, or either the right-handedness or the left-handedness. It's like, if I'm going to think about this is screw gauge, so think about it as a particle and it's going to have a spin. So when you have any object which is going to have certain spin, you can have two choices. Either this spin is going to be, and when the way I'm going to rotate this screw, it can have the right-handedness, either with the same spin it can have the right-handedness, and there is equal probability that it can be having the opposite way, left-handedness. So now, if in the beginning of the nature we were having this particular equal probability that for any given object, for certain spin, it can be either right-handedness or in the left-handedness, but nature choose to make certain choice. And the choice made by nature in the case of the weak forces was that it considered all the particles to be right-handedness. So there's something called symmetry breaking. Means it's a very interesting concept. So let me just talk about this.
Sir, if you mind, can I take a question, or would you take the question later? Okay. Somebody called Suvi Gyanodya is asking, sir, divergence of electric field is equal to charge density upon epsilon, but if charge is reversed, we get an extra negative sign that does not count the change in equation. I mean, so why it is so?
So here in the case when you are going to say divergence, there is going to be del. Okay, del is going to be chargeless. Electric field become minus E, and the rho density is going to be minus rho. So minus will cancel out on both the sides. There is going to be minus in the rho as well.
Absolutely. I was also thinking in the same way to give the answer.
Yeah. So
okay,
one can try to do these calculations are very interesting. So that's why maybe I have my notes I can share later once I have work out all these equation and conservations in my calculations. But I was just talking about this very interesting concept of something called symmetry breaking. I mean, I'll just try to give you a rough idea. Think about this object, this pen is standing on my hand. Now, till the point this object is lying over here, I am having, and this is going to have a choice to fall in all the directions. So the probability that it will fall in one direction is going, means there are all direction to have the equal probability. But the moment I'm going to leave it, it will fall to the one direction. It can fall this direction, it can fall this direction. So nature or this particular object, the moment I'm going to leave it and the moment I'm going to make any action on it, it is going to make a choice. Instead of, even though it was having the probability to go in any direction, it make a choice. It breaks there was a symmetrical distribution all around it. If you go talk about the probability of going in any direction, but it go in one direction, and that particular event of choosing one particular direction is known as the symmetry breaking. So same thing, why I'm telling you this, I'm just trying to say, even in the weak interaction, when the nature was deciding, and that's a question why this particular choice, but when nature was deciding the particles, like they are going to have a spin, any spin, whether they choose to have the right-handedness of any given particle or the left-handedness of a given particle, on the basis of that, they made a choice. Nature choose to have that all the particles need to be right-handed. And if they are going to, if we are defining, because it's a relative term, if we are saying all the particles are right-handed, then all the antiparticles are going to, sorry, if the particles are going to be left-handed, then all the antiparticles are going to be right-handed in it. So because left and right are relative terms. Okay, so that's why when we try to make any change, when you have a equation, of weak field interaction, then weak field interaction means the interaction between the leptons specifically, or the interaction between the quarks when we are going to talk about. So here I am talking about the electron and the antineutrino. When you make any change into the spin, their charge for a particle, let's say if I am having an electron will be a particle. It is going to have charge -1, but it is also going to have a handedness, which is the left-handedness, because nature have made that particular choice in the weak field. There are deeper theoretical reasons as well, but I'm just choosing to call it the choice of nature right now. Now, the moment you make a change in the charge, now charge electron will change to positron. Positron will be having charge -1 to +1, but changing the charge will not change the right-handedness. It will not automatically transform from the right-handed to left-handedness. So due to this particular change, because now you will be having an equation which will be having a positron, where the charge equation is going to be conserved, but there is not going to be a right-handed positron, which nature generally require in the weak field interaction. So that's why, due to this reason, because changing the charge will not inherently completely change the fundamental requirement of the theory. That's why weak interaction is generally not, or is not charge conjugate in that sense. Okay, so means electric field, if I'll go to the EM force, or if I'll go to the strong force, all these are charge conjugate, but my weak interaction is not going to be charge conjugate. Another such operation, I'm talking about mathematical equations only now. Another such operation is the parity operation. Parity operation is means in quantum mechanics. We must have seen this at many places. It's a very important operation which tells us a lot about the validity or the way our Hamiltonian should behave. But in general, parity operation would mean, let's say you have a particular object, it's in the Cartesian coordinates x, y, z. If you make a transformation and it to -x, -y, -z, if the system is changing from this particular state to another state and the system remains, or the equation of motion or the solution remains same, then we do call this particular transformation to be parity transformation. I'll try to give you this example, this exercise. This could be a good homework as well. I mean, though it's a very basic stuff for maybe first years and second years undergrad can do. So when you try to make a parity transformation in a Maxwell equation, then electric field is going to be -E because it's a polar vector. But magnetic field will remain magnetic. B will remain B. It will not go because there is something called axial vector, or you'll call it a pseudo vector. Okay. So in the transformation, when you'll make a parity transformation for a Maxwell equation, then the electric field -E B to B, rho will remain rho. But again, because J, which is the current density, is going to be J equal to rho V. It's dependent on velocity. So if X, Y, Z is changing, then the velocity will become -V. So J will also become -J. If you make these particular changes in the Maxwell equation, then you will figure out all four Maxwell equation will remain same. They will not change. One can try to do this exercise. That would be interesting to see. So means again, I'm just trying to say our Maxwell equations are going to be symmetric if you are going to make parity operation. Then if I'll talk about the Schrodinger equation, and in the Schrodinger equation, if I'm going to have a potential which is going to be, let's say, going to be a symmetric potential or a static potential, I'll say, be function of x. Even if I'm going to make that transformation over there, even Schrodinger equation is going to be symmetric under parity. Means that equation will not change. The formation of the equation will not change. So this way, I'm just trying to emphasize that there are, and again, remember this thing, when I was talking about charge, when I'm talking about parity, all these are discrete symmetries. Means you change xyz to -xy -yz, and then if you make one another change, you will come back. All these symmetries are twofold, very much like the reflection, or very much like the rectangle, twofold symmetries, and you'll come back to the same system. So our electromagnetic force, again, Maxwell equations are going to be symmetric under parity as well. Quantum Schrodinger equation is going to be symmetric under this thing. Again, when you talk about the weak field, it's going to be, weak interaction. If we start talking about, again, it don't follow due to the same reason. When the way I have told you about the right-handedness, due to the same reason, again, weak interaction doesn't follow the parity operation as well. The moment you will flip, that the corresponding helicity will not change accordingly in the parity as well. So consistently we are saying that force of nature, if you try to do this exercise for the force of gravity, if you try to do it for the electromagnetic force, which is governed by the electromagnetic equation, if you talk about the strong force, for these forces, parity, charge, all these are consistently invariant, but weak force is continuously violating it. Then we have one more interesting parity, which means I haven't written Maxwell equation for the reference, and someone want to do some calculations here. But again, when you do the third symmetry which I want to talk about is the time reversal symmetry. Time reversal symmetry, you make a transformation that you go from t to minus t or minus t to 2. It's again twofold symmetry I'm talking about. The moment you'll make the second rotation, you will come back to the same system. And most of the equation, whenever you write down a Hamiltonian, like say you write down a Hamiltonian or you write down a Lagrangian or you write down equation of motion for a pendulum, and you make that a particular transformation, time reversal transformation, you'll find out your Hamiltonians or your equation of motions are going to be independent of this particular transformation. Even again for the Maxwell equation, this slide I'll share. I hope each one of you can, those means especially the undergraduate student, they can try to do this exercise, that they will make all these transformation and see under all these transformation at least Maxwell equations are going to be time reversal symmetry they are going to follow. Okay, so means I have talked about three symmetries, C, T, and P. All these three symmetries come together and they are known as the CPT symmetries. Now, I have also said one thing, that when you apply another symmetry, let's say you have applied the C symmetry, charge conjugate you have taken. Now, if you apply after that the P parity transformation, if you are going to apply the time reversal transformation after this, these symmetries do combine together and they give rise to new kind of symmetries. So eventually, if you'll have a look, if I'll try to make a permutation combination of all the symmetries, then I can say there is always going to be the same state. Then there is going to be charge symmetry, then parity, because all of these are twofold symmetries, and they can also come together. Either they can be CP, CT, PT, all these kind of symmetries, and they can come together one by one. They can be, there is a global symmetry called the CPT symmetry. Now here I just want to talk about a very interesting feature, and this is very interesting in the sense, in nature, any theory, either any quantum field theory, if I'll just talk about any field theory that you want to develop for either for the electromagnetic force or the gravitational force, or you want to generate something based on some QCD, QED, or quantum electrodynamics, quantum chromodynamics, anything that you want to develop, there is one single requirement, that the Lagrangian or the equation or the action, which I'll talk about in a while, but the main equation which governs the equation of motion of the system, or the equation which governs the whole system that you write down for any system, that equation is supposedly need to be invariant under CPT transformation if they are applied together. This will be valid only this for this particular thing to be valid. The system need to have need to be Lorentz invariant. Lorentz invariant means when you go from in the quantum in the special theory of relativity, you have seen, you must have studied that when you go from one inertial frame to another inertial frame, all the laws of physics are going to be same. So similarly, if you have a theory, you change the inertial frame, then the theory need to be same. Then if you have locality, means there is another condition called locality. Locality means if you have a theory and if you are going to make certain changes in that particular theory, then the changes are going to be local. Local means it should follow something called a principle of causality. It means if you are making a change in the theory here, that theory, that particular information takes certain finite amount of time to propagate. That cannot propagate with a speed greater than c. Any information can't pass. So this particular feature, if it embedded in the theory, that is known as the locality, or any theory is going to be called local theory in that particular sense. And similarly, it should hold the energy conservation in that particular case. So this, what I want to emphasize with this particular symmetric CPT symmetry is that it is so fundamental to nature that even why is it interesting? See, when I'm talking about the electromagnetic force, when I'm talking about gravitational force, when I'm talking about the strong force, because they were individually following C, P, and T, means they were charge conjugate, parity, and time reversal, they were individually following that. But weak force, which was not following C, which was not following P, and due to which it will not also follow the T as well. This is again an exercise which I can see, I can give to you in a while. Even for the weak interaction, the CPT do hold. Till date, there are hundreds of experiments which are being done just to verify, just to check whether there is any violation of CPT. And when I do say, how do we check something? Okay, now it's very interesting to ask this question. Okay, sir, you are saying, oh, CPT is, how can I check whether some theory is going to be violated or not? So we've tried to figure out, the moment I'm saying CPT is valid, I'm talking about the Lorentz invariance, and then I'm talking about the energy is going to be conserved. Then in that particular case, if I'm going to make a transformation from particle to antiparticle, in that case the masses of the particle need to be same. There are certain set of tests in case this CPT will violate. So we go to the different detectors, like Atlas detector is there, or different kind of detector where we do these kind of weak interaction reactions, and we try to see whether there is a possibility for any violation. And till date, even experimentally, we don't see any signal of the violation of CPT theory. That's very interesting for me to just say that even if we do CP violation, means if you apply the parity operation, then after that you apply the charge reversal operation, CP violation we do observe, but CPT, that's not there. Okay, that's very interesting. One can dig deeper. Means it's very interesting. I have made certain notes as well, which was, I personally find it quite interesting to dig deeper. But I think I should move. So in this sense, what I was trying to refer to you, that till now I was just talking about the discrete symmetry.
Sir, I have a question from Pavanil, if you mind. Pavanil is asking, are there only these basic symmetries or anything more?
No. There are more. There are more. You can see, depending on the theories, you can find out. So when I was talking about, because I do have limited time, I was just pointing out to some very important. So these are the, if you'll do any particle theory course, or if you'll do talk about the any sort of you try to develop any other theory, the moment you start writing down equation, the important task would be to figure out these symmetries. These are the basic tests. Maybe you can write down a Lagrangian, you can have a particular system which might be having some more additional symmetries. There might be symmetries in nature which we might not be knowing, which I might talk a little bit in the end, which I'll tell you a little bit work where people are looking in the symmetries. But yes,
Absolutely.
There can be many more symmetries.
Sir, one quick question from Suvi Gyanodya. Sir, I have heard of Lorentz violation also. In that case, there exists more bigger symmetry, and in that case, CPT violation may happen or not.
Okay. So see, when I'm talking about CPT violation, so we do talk about something called standard model of physics, standard theory of physics. So in the general sense, whatever theory we are developing, the basic understanding of the universe, the basic theories, like in the case of general theory of relativity, I'm talking about GR. In that sense, we do have all these theories which gives us a best possible explanation of the universe. These theory, we put this condition, they should follow this particular parities, this particular symmetries. But in the literature, you find a lot many theories. Like in the case, I cannot tell you much about the high energy physics, but I can talk about the general theory of relativity. In that sense, you beyond the GR, you can write down a FR gravity, you can go into the higher dimensional theories, you can write down the string theories. The moment you can write down, means lot many theories which are beyond GR, means you want to extend, you want to see that whether the limitations of the theory that you are developing, the standard model that you have developed, that you can go beyond that, and can you look for something new. While developing those theories, your intention would be, oh, my theory need to be a little bit rich, so you can try to tune your system in such a way there could be some additional symmetries, because symmetry brings the beauty to the system, it brings the new information to the system. You can concisely frame certain conclusion about the system. So obviously, when you develop a new theory, or in the literature when you figure out certain new theory, you want some new symmetry to be introduced, while there are some basic tests, because standard theory of relativity is so well tested, and principle of Lorentz invariance, like when you go from one inertial frame to another inertial frame, it's so well tested. In case you are developing a theory which is not following the Lorentz invariance, then you'll doubt it. The day you'll write down that theory, you'll just send it to a reviewer for publication. He will, first thing he'll ask, okay, just go and check whether your theory is Lorentz invariant or not. If it is not, then that's the first no. That's the first thing that you'll see. So means there could be lot many symmetries, and that's how the people do go on deeper and deeper and try to figure out some new models and try to understand or give the explanation of the universe. Okay, and means I'm just talking about discrete. Now let's go to the continuous. You'll see there are the whole range of symmetries. It's not
So,
the
yeah, one quick question from Pavanit is that what makes them important? I mean to say, what makes the symmetries very important? If you can answer, we can.
Yeah, so what makes symmetries important? That's a very important question in that sense. See, when you try to understand something, like when you, if I'll just say energy is conserved, means in that sense, so that's a statement, you can observe it. But when you try to go on one layer down, why is it conserved? Why, when you start having this query about why, then we have to see that for something to be conserved, there need to be, nature should have designed something to be in that manner, otherwise that particular thing will not remain constant. And that particular something that universe do, the nature do, that is called symmetry. For us, symmetry is not objects or something. For this, the nature might have kept something constant. So see, think about why nature might have chosen that the electromagnetic equation, like our Maxwell equation, if I'll say, they are going to be invariant for charge. Either you solve those equations for positive charge or negative charge. That's a choice made by universe. It's not us, it's not mathematically we have done it, it's the choice of nature. And because we are talking about, when we are talking about physics, we are studying about all about the nature, it's the study of the nature. So nature have chosen it, and that has kept some symmetry in it. I'm calling this charge reversal. So it's important for us to know and make certain inference out of it. So that's why everything that we do see, all the mathematical equation that we do derive, these are based on these symmetries, and that's the beauty of nature. And it's interesting for us as well. So if you go in, when you will, maybe some of you might be working in the high energy physics, still people looking for the violation of CPT. So in the sciences, even in my theory, if I'll talk about, I have recently written a paper where I have just working on something called a model called FR gravity. It's an extension of Einstein General Theory of Relativity. But when I'm looking for some alternative of a theory, I'm not just directly questioning the understanding of, or the understanding developed by the Einstein General Theory of Relativity. My intuition is to explore further. So these symmetries are helping us to explore further, look deeper in that particular sense. So in that sense, that's why maybe by the end of this talk, I'll be able to convince you better on this. So why is it important? So
right, absolutely. Yeah,
I can just
thank you, Professor, for answering. I will go back to the slides now because we have to finish it off and then take the further questions. Yeah.
Okay. So now, just I haven't talked about all about the discrete symmetries, but just by having a little bit flavor of all these different discrete symmetry, you can see they are just directly relating us with the very fundamental understanding, very fundamental forces. How does our nature behave? Certain features of the nature it is telling us. And this is just the discrete, where we are making some finite amount of changes. Now, can you even imagine, like, if I'll start talking about something called continuous symmetries? Means continuous symmetry means where I can make any finite amount of change to my system and that system remains same, something of that sort. And the moment the moment we start looking at it, just going to give us some amazing results, some amazing understanding of the that we'll get. So here I am just changing my course from discrete symmetries to the continuous symmetry. And the moment I'm talking about something called continuous, the first thing that comes to anyone's mind the moment you're doing physics or maths or some sense, if you want to talk about something continuous, we have to talk about in mathematical terms, and the mathematics that we use to study the change in any continuous system is the calculus. So you cannot study the continuous symmetry or any continuous change in the system without the understanding of the calculus. So obviously I cannot teach calculus here, but I understand that all of you must be having good understanding of the calculus. But what I can talk about, that a very little bit features that we generally use. So I was giving this example. when you, let's say you have this pendulum, I'm oscillating this pendulum like this, consider it to be a pendulum. Okay, now when this particular pendulum is oscillating, if I am going to solve the equation of motion, or write down the equation of motion for this system, I'll write down a kind of a free body diagram, and then going to make the force equation and everything. But there is one alternative approach as well. We call that approach to be something called Lagrangian approach, in which instead of talking about studying the system from the force point of view, we study the system from the energy point of view. And we define, in that particular system, we define a quantity called action. So sir, should I take action to be considered, or like should I talk a little bit about action? Dr. Shona?
Yeah, you can just give a brief overview, because okay, these and the Euler-Lagrange equation, I think any graduate will know.
Yeah. So now for solving any system, when you are talking about any system, we define a quantity called action. So this action is a very interesting stuff. So this action you can think about, like, let's say, let me put it in this way. Let's say I plan to go from here, Delhi to Kolkata. And now if I am planning to go from Delhi to Kolkata, then there can be infinite number of ways I can choose. There can be infinite number of paths. I can go through different routes. Now, every route, when I'll go, is going to have its own difficulty. Some routes might be taking a very less amount of time, but the less amount of time, but might be having very difficult terrain, might be having hills and all sort of difficulties. Some might be taking large amount of time, maybe taking large amount of time, in the sense the path might be very straightforward, going by road, but that might be taking a lot of time. 2 points, a terrain can be where in some way there is going to be a lot of zigzags. Zigzags means when you are going to have zigzag, again you have, if you are driving, then you have to put acceleration, sometimes you have to deaccelerate, change the velocity. So means, depending on the path that you are going to choose, if I'll give you the freedom that every time you'll go from Delhi to Kolkata and through all the parts, every time you put a score on that part, and the score of convenience, how easy you put a score on it, like a number. Okay, and depending on if it is very convenient, you will give it a number. If it is very hard for you to go from point A to point B, then you are going to give a number. So this action in somehow is that mathematical score that we give through in a mathematical manner to any trajectory. If you are going from one event at a time t1 to t2, then you are trying to put some score on it. And nature does the same thing. It put a score on all the objects, all the paths, and then eventually choose a path which is the most optimum. Most optimum doesn't mean that it's going to be the least time, or it's going to be least distance or something. The path which is going to be overall is going to be most optimum, for which is going to be the most convenient path. And for a most convenient part, we want that this number, when you make slight change to this particular term s, this variation, if you make slight variation to it, it should not change. So that's why nature choose to have a trajectory. When you try to study a system and you want to write down want to see which path it's going to, which trajectory it's going to follow, it will follow a trajectory where this action will not change significantly. So you choose that delta s to be 0. Any theory which is going to be, nature will choose a theory where the change in action is going to be negligible or equal to 0. So if you do this, we can easily come up with this equation called popular Euler-Lagrange equation, which is written to this. Now, why I'm telling you this? Now, in the continuous symmetries, whenever I'm going to, from this point onward, whatever I'm going to talk about, you will see this particular action is going to have a term called Lagrangian, and that Lagrangian is again the function of some generalized coordinates like position coordinate or q dot, you can call it. Talking about the mechanics, it's like position, and then you are talking about velocity, and then the time. All these things you are talking about. If I make certain symmetric transformation in these parameters, if I'll change q to q plus some delta, or q prime, or this q dot to some q dot some delta time, or time t plus some delta time, if I'll make these transformation and then this action remain invariant, so that would be a new symmetry for me. So then I can say, if in my action, if I'm changing these particular generalized coordinates or the coordinate on which this action do depend, if I make certain changes in these and still my action is remaining same, then I'll call it that this particular s or this particular action is going to be invariant under this operation. So remember, I told you about these two terms. what we change and in what we do change. So we are changing some coordinate. Here I am talking about some generalized coordinate. You are making some change in that generalized coordinate. And then second thing is I am making those changes in action. So operation is going to be in a particular generalized coordinate, and then change is going to occur in the action. And if making that particular operation remain, keeping my action constant, is not making any change, then I'm going to say that my action is going to be symmetric, or going to be invariant under that particular operation. So that's the terminology I'm going to use. Instead of going this, I'll just try to give you one simple exercise, because we all have done this pendulum. So like simple harmonic motions from the first year, so 11th class onward, we do start talking about it. And so that's the easiest example that I can give. So when we try to write down the Lagrangian, which is nothing but the kinetic energy minus the potential energy, with the trade-off between the potential and kinetic energy, if we'll talk about, then this we can easily write down this section. What I am just trying to tell you, write down a Lagrangian, and if I write down the Lagrangian, obviously you will be able to write down the action. And I have done this simple calculation, if you'll go through that, I have made a transformation, because if you'll see the Lagrangian, that is going to have x dot, so which is going to have a time derivative, which is the velocity for this particular case. If I make a transformation which I'm going to time translational, means if I transform my equation from t to t prime, where t is t plus some epsilon, if I make that transformation and do little bit calculations, there are going to be, you have to do the whole derivative of L, you have to take, and if you'll see this delta x equal to, this is the basic definition from the first principle of derivative, like of differentiation. So by using these simple changes, a little bit algebra is required, I can easily prove that the delta s, if I make a change from t prime to t plus epsilon, my delta is going to remain same. What I can claim with this, I am claiming for a simple harmonic oscillator, if I am making a time translational change, if I am my time in translating from t to t prime, in that particular case, action is remaining constant. And because my action is remaining constant under this particular transformation, I am calling this symmetry of action to be the time translational symmetry. This point is clear. Now, interesting point emerges. Someone asks, why is it important? Now, it's important for this reason. If I consider this, and if I'll write down this Lagrangian, I can write down this Lagrangian, I'll write down the canonical canonical potential, and then convert my Lagrangian into the Hamiltonian. When we try to do this simple calculation for a simple harmonic oscillator, we figure out that for this time translation, dH by dt is going to be 0. For this system, dH by dt is going to be 0. What does it mean? Means for this system, the Hamiltonian is going to constant. The energy is not changing. So this simple exercise, where we are seeing that our Lagrangian was time translation, going to have the time translational symmetry, it is having a consequence as well, and that consequence is coming into the mathematical equation in the terms of the conservation of energy. It's just for the simple pendulum, and each one of us know that the whatever you'll do, if there is not going to be any perturbation, the energy of a simple harmonic oscillation is always going to be constant. That energy is going to be conserved. So this is the symmetry refers to the energy conservation. Energy is conserved in an oscillation because there is time translational symmetry. So I can say this. I'm going to give you few exercises on this. I'm not going to do this exercise. Take the same Lagrangian. Now, instead of the time translational Lagrangian, in the same Lagrangian, make a transformation on the space part. You go from x prime to xi plus some delta. And then you can, similar to this, you can prove that there is going to be momentum conservation. If you, because my Lagrangian is in the one-dimensional 1D, if I'll talk about a Lagrangian which is going to be in 3, let's say in a spherical coordinates, let's say I am writing down a Lagrangian for a object or a planet or a object moving on a circular path or on a spherical path, then I have to write down my Lagrangian on in the spherical coordinates r, theta and phi. In that particular case, if I make a transformation on the r radial part and I'm just going to rotate it, in that particular case, you will figure out that Similarly, when you solve this for Lagrangian, when you solve it for action, when you're going to write down your Euler field, Euler Lagrange equations, you will figure out angular momentum will also turn out to be. Maybe in the classical mechanics or in the first year classical mechanics courses, each one of you might have done it. So eventually what I'm saying, that when I'm writing Lagrangian, I'm making it some transformation. Making this transformation, time transformation leads to energy conservation. When I'm making a transformation in position, it's leading to the conservation of the linear momentum. When I'm making a transformation on the rotation part, my Lagrangian, my action is going to remain constant, and it's leading to the something called the angular momentum conservation. Isn't it interesting in that sense? Now, these features that we do talk about the nature.
Everybody is enjoying, sir. I got a comment from somebody called Sauratana Roy. He is telling, wow, the discussion is fascinating, but unfortunately, I do not have the mathematical base to understand. I'm currently pursuing BSc Physics from Presidency University, and I'm first semester now. And he has given a heart sign, so it shows that everybody is enjoying. Thank you for the fascinating.
I hope it's not long. So maybe in a year or so, you will be talking about all this stuff. Maybe second year or third year, you'll start studying about quantum mechanics. All these parity and everything will come into reality. Okay, and you'll be talking about in the first year, you'll be studying special theory of relativity. Over there, you are going to talk about all these Lorentz invariance and Lorentz boost and everything. So very quickly, you'll be learning about all this.
Yes.
So now this is interesting here. So what Noether predicted that for corresponding to every, like whenever you are going to have, see, remember this, when you are making these changes in the Lagrangian, they are continuous in manner. Means you are making very slight change in time, very slight change in position or rotation. All these are continuous in nature. And when you are making this continuous nature, they are leading to something called some conservation law. So in some sense, this gives a hint to Noether as well, though these conservation laws were all there. But Noether figured out a idea, and this she stated it. It means though these conservation were over there, but she kind of put it in the terms or put it in writing that corresponding to every continuous symmetry, when you are going to have a action which is going to have continuous symmetry of action, corresponding to every continuous symmetry, there is going to be associated conservation law or a conservation quantity. Okay, so that's way it's interesting. I just want to talk about one more very interesting conservation quantity, which because everyone might have done it in the classical dynamics, all this, but one very interesting conservation principle, which is the.
So we have a quick question from Sankalp. In which situation or system does time translation symmetry break?
Okay, I hope Sankalp, for that you have to wait till the end of the talk. The last example that I am going to talk about is going to be the violation of time translational symmetry.
Yeah. Okay. Sankalp, please wait because sir is telling that he will be explaining it. Yes, thank you, sir. Please go ahead.
It will be covered. Okay. Now, maybe this might be a little bit of a bit advanced, but I just want to, means for the UG students, I'll say, but some of them might have done as well in case. I hope each one of you are familiar with Schrodinger equation. Okay. Now, Schrodinger equation is an equation of motion for any quantum particle if it is going to be non-relativistic in manner. Then, obviously, that equation of motion, if you go into quantum field theory, then that can also be derived, or that also can be developed through a field equation approach, where you will write down a Lagrangian. So I can say that Schrodinger's equation is nothing but if you have this Lagrangian and solve this Lagrangian by using the Euler Lagrange equation, the output is going to be over Schrodinger equation. So it's the Lagrangian for the Schrodinger equation. So it's a where psi is the wave function, which we just talk about for any, there is going to be wave function associated to any system in quantum mechanical system. So consider this to be Lagrangian, and if Lagrangian, you can write down corresponding action as well. That's there. Now, interesting feature is that there is a very interesting kind of symmetry in it, which is we call the phase transformation symmetry. Means if you have a wave function psi, Now, if you make the slight transformation in the phase, so if you want to make some change in the phase, you are going to put a e to the power I alpha, because that's going to be the phase part. In the magnitude, if you want to add certain phase, you are going to make certain change in this e to the power I phi part. So if you make that particular transformation in the wave function, so either you choose a wave function psi, or you transform it from psi to psi e to the power I alpha, where alpha is some constant. Remember this, alpha is some constant. If you make that transformation and put that particular wave function in your Lagrangian and then try to solve it for the action, then you will realize that even for this particular transformation of your wave function, the system will remain invariant. The action will remain invariant. Now, if action will, so one would ask, okay, this also is symmetry, because your wave function, you are making a transformation in the wave function, but the action is remaining same. So what does it signify? You can write down, instead of this Lagrangian, the one I have written it for the Schrodinger equation, one can choose to write down a Lagrangian for the electromagnetic field, like 1 by this f mu nu Lagrangian, complete Lagrangian for any scalar field in the electric field, in the electrodynamic manner. Over there, if you'll try to do the same phase, then you will figure out that also going to be the invariant. So I haven't shown the electromagnetic part, I'm just showing you only the Schrodinger or quantum part of it. If you make this transformation corresponding to the probability distribution, if those of you are aware about the quantum dynamics and the property of wave function, corresponding to the any wave function, we define something called the probability density. And eventually, when we talk about this distribution of probability, then we talk about when a wave function do evolve, one do ask, okay, then what does it evolve, what is flowing? So the quantity that do flow, we call it the probability current density in the case of the quantum mechanics. And that probability current density, the net of that particular probability current density should be 1. So if you are familiar that for a normalized wave function, the total probability need to be 1. So in the case of a wave function, probability is the total charge. Okay, in the case of electromagnetic system, the charge, the electric charge that we do mean that's the real charge. But in the case of quantum mechanics, when I'm talking about a wave function, for me the total charge is probability, and the current density is the probability current density, the probability of going from x to x plus delta x, in the way we do understand the quantum mechanics. So we try to verify here, one can try to do it very easily, that when you make a transformation in the wave function from psi to e to the power I alpha psi, we end up with this particular del mu j mu. So because it's I'm writing it in the tensor form, because otherwise it will be very complicated to write down. Means in the sense, means tensor do help us to write down this particular del mu j mu is generally known as the conservation law of conservation, or the conservation equation. And this particular quantity needs, so if I'll just write down, this is going to be 4 vector. J mu is a 4 vector. 4 vector is going to have 4 elements in the vector. First element is going to be the time element, naught element, which is going J naught, which is representing the corresponding to energy, and the remaining 3 are going to be time like, which is going to represent the time component, and then there are going to be 3 other components which are going to be spatial. If you are familiar with the 4 vectors concept of 4 vector in the special theory of relativity. Okay, now if I'll try to write down this, we figured out the quantity which is going to remain constant is going to be charged. In the quantum mechanics, the probability, so this is very fundamental. Even the definition, when you in the quantum mechanics, you explain the Hilbert space, then that's the must condition that your wave function and the system need to be normalized. That condition is also coming from a symmetry. The condition that your wave function need to be normalized is coming from a global symmetry, where your wave function is going to, if you are going to transform a wave function from psi to psi e to the power I alpha, this is coming due to this particular symmetry. Even in the electromagnetic theory, this symmetry gives rise to something called charge conservation. Okay, so this is also one very interesting symmetry, and these symmetries are global. When the way I'm saying it, it's a word called global, means anywhere, any law, anything that you will do in any mathematical system that you will develop, any theory you will develop, these are going to be valid. Okay, violation. Someone asked about the violation. I'll come back to that. So let me right now make this statement that these are global, and let us consider them to be global for now. Only the violation I'll talk about later. Okay, so I am calling them global because they are going to remain valid across the theories. Now it gives rise to it gives me a different curiosity it develop in our mind. Is that time symmetry, energy conservation, space symmetry, momentum, rotational symmetry, angular momentum, internal phase symmetry is leading to the charge conservation, and these are global symmetries. Can we have something called local symmetries as well, or local transformation as well? Means I am making a change in the system locally, means at one place. It's not global change in the system, it's on one place. So it's very much like, let me just try to take this analogous. It's not the exact verification. It's very much like all of us are sitting, some of you are sitting across the world. Let's say we are sitting and someone threw a projectile motion. Now that projectile motion, when you are throwing, each one of us has the freedom to choose our own coordinate system. You can choose their own coordinate system, though each one of us are going to have their different coordinate system, but the trajectory and the path, that particular, or the result, or the projectile motion, or we'll say this is going to follow a projectile motion, that motion is going to be the same, independent of the choice of coordinate system you, me, or anyone sitting anywhere is going to take. So means if we are going to have this freedom as well, so this is a great freedom, the freedom to have their own coordinate system. That's a great freedom to have. Similarly, we can have different kind of these local freedoms in the systems, where each one of us at our own convenience, we can make those certain choices at different position on different times. And then even if a system can accommodate this much of freedom, that would be really interesting to see. So what I'm going to do, we are going to try to figure out some of those kind of local symmetries and the beauty behind the local symmetry. So just try to be clear. We are talking about continuous symmetries. There are going to be two classifications. One is the global symmetries, where changes are going to be independent of the time, place, and time and the place, or any position of space time. There is going to be local symmetries, which are going to be very much function of position or time. Okay, at least the position let's talk about. Okay, and let's try to explore that particular domain as well. So what I'm going to do, I'll talk about something called local symmetries, which is another kind of continuous symmetry. What change? If you'll just figure out, this is very interesting. If you'll figure out this particular expression here, I am transforming psi to phi e to the power I alpha, and I was assuming alpha to be constant. Here I am not doing that. I am transforming psi to some other psi to psi prime in such a way the phase difference that I am making is e to the power I alpha, but this is a function of x. So the transformation that I am making, that's not global. That depends on position. At position A, position B, across the space time, everywhere, this transformation is going to be different. And that's why I'm calling it local transformation, local symmetrical transformation. Now, one thing is very interesting in nature. Because two very basic laws, the law of gravity and the electromagnetic radiation, which we can very easily study, at least the law of gravity, so we can easily study. We figure out that even if we make these local choices in our system, still our theories remain invariant. Theory will not change in case you'll make some local transformation in your wave function. So it makes us to think, like, if I want to develop a theory in such a manner, and in such a manner that if I'll make certain local transformation in my equation of motion, those equation of motion should also not change. If this is the observation, if the nature had chosen to have a choice that these local transformation, choosing the coordinate system here, so it will not change the nature of it should not change the physical phenomena. Law of physics are not changing in reality. We don't see any feature. So it becomes a pressure on the theoretical physicist that you should also develop a theory which should be having equation which are invariant under it. So that's a reverse thing. Sometimes you develop a theory and go for the test. Here it's a feature that we are seeing. Okay, local changes are not changing, so we need to make a make our theory compatible with that particular thing. Now the challenge that we face here, it's very easy. If you'll follow the equation, I can always take the time derivative of this wave function psi x. The moment I'm going to take a simple partial derivative of this psi x, this is going to have del psi x plus this additional term. If you can see, this is going to be iota del mu alpha. I'm talking about you are making a transformation. The moment you are making a transformation, your del mu, the gradient, is changing. If you look back into this particular equation here, if you'll take the partial derivative, your equation will remain same. I'll show it to you again maybe. But here, when you are making this transformation, you are getting this additional term. I'll just try to give you an analogy. It might looking very mathematical right now. This particular term, if we keep this particular term, and if I'll just try to put it back in our system, when I call system, I mean the Lagrangian and the action, the system will have some absurd behavior, some absurd additional quantities we don't know in this nature. I just trying to give you a very close analogy. Let's consider that you are sitting in a system. Let's say we are in an inertial frame, and another frame, which is, let's say someone is moving in a car and car is accelerating, means the moment I am talking about it's accelerating, it's a non-inertial frame. So when you are going from inertial frame to non-inertial frame, and if there is going to be a pendulum or a ball you'll throw, then you will additionally see that until unless you have to take care of a pseudo force, the Coriolis force or the centripetal force that we generally talk about, that to accommodate this particular, because only the frames are changing. You are going from inertial frame to a non-inertial frame. In that particular case, a additional term, a additional force in the mechanics approach at least, turn up in our theory, which is a pseudo force. So means there are something additional which we have to account for. Now, similarly, means it's not exactly the same explanation, but I'm just trying to give you the analogy because you can easily relate with that. Similarly, here I can come to, So here I am trying to talk about this. When I'm taking the first derivative, we are getting this additional term. And if I want to keep my action or my Lagrangian or action invariant of this particular transformation, we need to figure out this pseudo kind of additional feature that can solve our equation. Okay, what do we do? That's a very easy mathematical thing. If this is additional term, add something which can cancel it out. That's what we do. When you have a system, when you have in your non-inertial frame, when you have a motion, when you are not able to explain the motion, then you put a pseudo force. You define that there is a presence of a pseudo force even in your field equation, even your force equation in the free body diagram of a system, you put those pseudo forces. Similarly, because you want to counter that particular additional feature that you are seeing in the system. Similarly, here in this equation, because we want to counter this additional term that was occurring in the derivative, we put some additional feature, and that additional term we put here. I am adding this term to be something called IQA mu, means A is here in this particular theory. I am putting this A. A is nothing but the vector potential from the electromagnetic theory. Okay. If I'll put this where A is going to transform like this particular form, A mu 1 by Q, if you can have a look. If I'll put this term and change my transformation, this partial derivative, I change it into something called the covariant derivative. So this covariant derivative is nothing but you have a proper derivative, proper partial derivative plus some correction. So proper derivative del mu and this particular correction, that correction is coming due to, because this is occurring in the theory because your system is going to, you want to connect two different points. See what I was talking about. Now you are having, let's go back to the same example of projectile motion. You are having a coordinate system. I am having a coordinate system, but there need to be if I am saying that the physics is not going to be depending on your coordinate system or my coordinate system, then physics will remain same. Then your coordinate system and my coordinate system should be having some formula or some way to transform from your coordinate system to my coordinate system, which we do generally do in physics very easily. Similarly, here I am talking about, because we in a complete space time, every point is going to have a different phase, because phase is a function of position. So there need to be some correlation between these 2 points. So this additional term is nothing but it's a correction. Maybe those of you might have done a course on the GR, they might have seen the same thing, same explanation of covariant derivative we give for the this parallel transport when we move from the on any curved surface. I'll talk a little bit about that, but that's also in the GR point of view. Here I'm talking in a slightly different manner.
The parallel transport is basically when you're transporting along it, and when the two vectors come back, it shows there is a difference. That means we are working on a space-time curvature. If it overlaps, that means there is no curvature.
Yeah.
So we have a question, if you can allow me.
Yes,
I think that this is a little bit off topic, but I hope you can take it forward how to answer. Ayab is asking, sir, what is the role of Dirac propagator?
Okay. See, eventually, when Dirac propagator, or you can see when you write down your Maxwell field equation in a particular manner, means you write down this Dirac operator. When you write, it's nothing but a smart way of writing down your equation, and there are certain operations which are, means it's not only going to be a particular quantity, like it's not going to be only the covariant derivative, it's not only going to be the simple partial derivative. We always figure out certain operators which are going to be more significant in the manner, let's say, I'll say if a particular equation is going to have multiple operation, like it's going to have derivative operation, then it's going to be 1 by c and derivative with respect to time, with respect to position. Somehow when you combine this whole operator, the time dependent time derivative and the position derivative together, and then apply on a particular system, so this whole thing acts as a individual operation that gives a certain feature. So it's somehow we find out that instead of applying two operations separately, we combine a package, and that package is so effectful, like that's giving us more result in more easier way. So means that is one of the way I can put in. Maybe it can
I think that, say, for example, we can also say, sir, if you allow me, if a particle is, for example, starting at point A in space time, what is the amplitude or the probability amplitude that it will be to find in particle B? So it is like a kind of a GPS route to describe how, particles in quantum state travels from one space to another. And as you have rightly told, that it is a smart way of writing, so that we don't have to write it too much.
Yeah. So so that's a better explanation. Okay. Maybe when sometimes you quickly don't get the way of
absolutely.
Yeah.
So he is asking the same question. So does the Noether's coupling has relation with action?
Noether's coupling. So means obviously, though all these means when I'm talking transformation, any coupling in the word, in the sense Noether coupling means it's talking about the transformation or what? Means all these particular
the transformation, transformation.
Obviously they are very fundamental to the action. If I'm talking about any sort of transformation of all these particular transformation, they are going to eventually lead to some Noether currents which we calculate. Those Noether currents are going to have means how do you get a Noether current? So Noether current, if you say the way we calculate the Hamiltonian or something, so those Noether currents are going to be derived from the our traditional action, and then you'll write down the Euler-Lagrange equation. So obviously it will have. So eventually in the Noether current, all these couplings will turn up. So it do have. Okay. So if coming back to the topic, what I'm trying to tell, in this particular case, this is very interesting to figure out that if you are going to have a local symmetry or local phase transformation in your system, then if you want your system to be invariant, then you have to give a channel to your Lagrangian or to action where 2 points in the space can communicate with each other. See, this is the important point to understand. When you are having a local symmetry, at every point there is going to be a different kind of phase transformation. And now if I am saying my action is going to be invariant under that, then we have to provide a channel through which you can communicate from point A to point B, point B to point C to. So it provides us a channel to communicate where the communication can happen between the space. And when we to talk about this channel, so it provides us a field. So that's the definition of field. Field is nothing but a channel through which different point of the space time can communicate with each other. That's how we define a basic crude example understanding of the field. So what we are trying to say, that if I am if I am seeing that in my action there is a local invariance, then for that local invariance we have to have some sort of field. And why is it beautiful? The beauty of this is that if you are going to write down this particular equation for electromagnetic theory or for quantum field theory per se, then that field turn out to be the electromagnetic field. If I am writing the same thing for the in the general theory of relativity, that field turn out to be a gravitational field. When you write down it for any potential, any quantum field theory where you have certain scalar field theory, then it is going to be a particular scalar field. So your local symmetries make or gives you the freedom to have the field in a system. And you can have another approach and that's why whenever a theory will have this kind of freedom, we call those theories to be gauge invariant theory. So this particular means you might be listening whenever you go through a particular article and say, oh, this theory, our theory is gauge invariant theory. What does it mean? Gauge invariant theory means that your theory has the freedom to have a field, and it is nothing but it gives, as a user, it gives us a freedom that you can choose your own reference. And there is going to be a mechanism through which you can go from one point to another point in the space time through the field. So where our global symmetries were giving us the conservation laws, our local symmetries are providing us the channels through which the space time can communicate, and those channels we are calling them the field. So it's the interesting stuff. Global symmetries, laws of conservation, and the local symmetries are giving you the fields. You have the, like in the case of electromagnetic field, we do have the this whole EM interaction through the photons. When you have the gravitational field, then when you have a general theory of relativity, you put the gravity, you require a field that's going to be the communication through the gravitons. If you are writing a Lagrangian for your weak field theory, then you are weak forces or weak interactions, then you require the mediating field that is going to be over WZ bosons. If you are going to talk about the about a strong field, then there are going to be gluons, and the communication between the quarks, that's going to be through the bosons, but it's otherwise it's going to be the gluons. So in this way, in all the theories, if you are writing down a Lagrangian and you are just any theory, means because you have eventually you have only any system you write down, we have these four forces, gravity or EM, and then the strong and weak. Either you can merge them and you can make some new theory, or gravity of theory of everything, on all these kind of stuff. But every theory should give you a field, and that field is going to provide you the whole information about the system. So you the moment you'll write down, so that's a mathematical exercise, the moment you'll write down a Lagrangian, first thing would be to figure out whether this particular Lagrangian is invariant under the whether it's the gauge invariant. When I'm saying the word gauge invariant, it means that whether it's invariant under this particular local symmetric transformation or not. Okay, so it's a means I thought I'll give you the idea. Means this is the same idea which Dr. Shonak has already talked about. The way you have a vector, and when you try to move this, let's say you have a vector on this particular sphere, on this sphere like his. If you are going to want to propagate this vector from point A to point B, when it will come back, take the whole rotation. If you are going to take only the derivatives, like your partial derivative, every time the direction will keep changing. Means direction will remain like this overall, and when it will come back, it will not come to the same point. So every time you are going to go from point A to point B on a sphere, along with the transformation, you are supposed to make a correction in your derivative. So the additional part that you do see in the covariant derivative, that's a additional term which makes this vector, that when it will start from point A, it can come back to the same point in the same manner. It's the same
Yeah,
thing.
the basis of the basis of the vectors actually change, which doesn't happen in Cartesian coordinate, and this is actually used by correcting using the Christoffel symbols of the first and the second kind.
Yes. Okay. I'll be briefly talking about that as well. Sorry. Okay. So I mean that's why means eventually, if you are talking in the terms of whenever you develop any theory, any Lagrangian you write down, and the moment you want to make any local transformation, and when you take the derivatives are going to be covariant derivative, because in the until unless it's a Minkowski space, means which is it's more like a Euclidean space, flat space in that sense. Otherwise, any curved space, if you are going to talk about any space time which is curved, you have to the derivatives are going to be covariant derivatives. Okay. Maybe I'll briefly talk about it. So that's the whole stuff. Now I'll go to, okay, I don't know whether I should talk much about this particular thing, but I'll just give you the idea. I made a very claim that the language of symmetry is group theory, and you will be surprised that when I was talking about the discrete symmetries, then I was talking about the groups, all those Z1, Z2, or different kind of groups. Even for CPT, I made that particular group. Now, when I'm talking about this global or the symmetric or continuous symmetries, I haven't talked about the groups till now. But eventually, because when I'm making a transformation, even a simple rotational transformation like this, there can be infinite number of transformations because it's a continuous space. So you can keep having a group, and the size of the group is always going to be, so all these groups are going to be infinite groups. So the groups under the continuous symmetries, those groups are named by something called Lie groups. So there is a complete dynamics of the group theory, which I am not having the freedom to go right now. But in the group theory, all these particular if you will have a group, so in the you will put all those particular transformation together, which are going to be infinite in number, which follow the properties of the group, which we talked about when we were talking about in the beginning, and then you try to study in that particular term. So again, the moment you are going to talk about any theory in the means, when you go and study in the literature, mostly you will be finding out in the terms, will say, oh, a particular theory, let's say if I am going to talk about the Lorentzian transformation, you will going to be say that this is SO31 theory, means there is a particular spatial orthogonal group. So spatial orthogonal group, it means there is going to be a kind of operation, all those phase operations which are going to be unitary in nature or going to be orthogonal in nature, all those operations are going to allow this kind of transformation to happen. Different forces, different theories, when you merge two symmetries together, they will give rise to a new group, and that group might be having a different dimensions. Depending on the size of the dimension of the system, we put these numbers 1, 2, 3. So here U means the unitary, SU means the spatial unitary. Unitary means quantum mechanics, each one of us know that the unitary transformation UU transpose is going to be identity. And when we call it the spatial unitary, we say that if we make this determinant of this U matrix, if it turn out to be +1, we start calling them spatial. Otherwise, we call them U1, U2, U3. The moment because any unitary matrix, if you'll take, its determinant can have +1 value, -1 value. If both are the choices, we call that the unitary. The moment determinant is +1, we call them spatial unitary. Similarly, we do have SO groups, which are orthogonal, where when you make the transformation, but in the real e to the power I alpha, it's going to be real transformation. Then you start talking about space orthogonal or spatial orthogonal. Depending on the theory, like when we talk about the weak theory, in the leptons corresponding to every electron, there is going to be a neutrino or anti-neutrino, like per se. So it's a double fold theory. So the matrix or the transformation that you are going to have, like for example, if I'll talk about the spin of electron, for spin of the electron, we have this. If you have done quantum mechanics, then we do have these polymatrices, sigma x, sigma y, sigma z. Now, means if you want to make transformation in the spin of an electron, then you have to make a change through those sigma x, sigma y, sigma z, which are going to be 2 by 2 matrices. Now, all those 2 by 2 matrices, we call them, and those are, one can try to do exercise. You take the poly matrices and then try to find out their determinant and everything. We'll figure out that could turn out to be +1. So that's why we put them under the class of SU, spatial unitary, because we talking because they do have the imaginary terms. That's why unitary. Had they been having all the real terms, we'll call them the orthogonal, like simple rotation, cos theta minus sin theta cos theta term, like the simple rotational transformation, that's known as the orthogonal term. So when you do study any topic, any book in the go to the continuous symmetries, you will find out again the language is going to be group theory. If you listen the lecture of someone giving from particle physics, or someone teaching you quantum field theory will be teaching you higher energy physics, they will not be talking about this individual symmetries. They will be saying, oh, this particular transformation is having this particular Lie group, U1, U2, U3, merge to SU multiply S3, different kind of symmetries coming together. So that way, the language again for the continuous symmetry is going to be Lie group. I think that could be a completely new topic which can be taken separately. So I'm just giving you the idea that I'm not going into the details and properties of Lie groups, but just want to introduce you with the groups of continuous symmetries putting together. Okay. So now, what did Noether do? All these things were all there in open. At least all the global symmetries and their conservation principle were all there in the picture. They were live and everywhere available. Then what was the contribution of Noether? Noether framed them. Noether gave them a definition. Noether proved that they are consistent in nature. So Noether made her statement. So these two things one need to remember. Noether's theorem are only for the continuous symmetries. Noether's statement doesn't apply to the discrete symmetries. This is the first thing question I'm going to say. What does she? And now, because even in the continuous symmetry, I talked about the global symmetries and the local symmetries. So her laws are going to be about both of them. So first statement that Noether gave, and the thing that we have proved as well mathematically, calculation wise, I have given you homework as well to prove that corresponding to every global symmetry, there is going to be a conserved symmetry. Oh, sorry, conserved quantity. Time ke corresponding, then energy, space, then there is momentum, rotation, then angular momentum, global phase change is going to be charge conservation. This is about the first. What does she say about the local symmetries? She said that corresponding to every continuous local, this thing means in the literature you will find out local symmetries, we do call them the gauge symmetries as well. So this terminology one should not confuse. So gauge invariance, gauge symmetries, all these things are about the local symmetry phase transformation. So corresponding to continuous local symmetry, the statement is that whenever you are going to have a action which is going to be invariant under the continuous local symmetry, then that system will require a field and a gauge field, and we call that particular field to be gauge field, and that theory we do call the gauge invariant. And why I'm telling you this, I still remember when I was in my first year, third, or even during the graduation, I used to listen lectures, and professor used to come, and even my seniors, even in the first years of PhDs, like even though I have studied courses on electromagnetic theory, I was aware about the gauge invariance and the all Coulombic invariant gauge what we study in the electromagnetic theory. But whenever they used to say, oh, we are writing this Lagrangian, this is gauge invariant, this is gauge field, and all these definitions, suddenly I used to find it as slightly tricky to register immediately to understand the whole essence. What does it mean about this theory? So I just want to highlight this point. When you talk about, whenever someone say, oh, this is a Lagrangian, when it is going to be gauge invariant, it has a gauge field, it means that particular Lagrangian is invariant under the local symmetric transformation. That's what it means, where you can, and it's nothing but it gives you the freedom to choose your reference. So means it's very much like when you are developing your theory, you can sit in any reference frame any reference frame. You can change frame here to there and the physics will remain same. So that way, as a user, you have the freedom to change the reference frame. And global this gauge symmetry gives you the choice that in whatever way you want to study your system, do you study, choose your reference, choose your where you, how do you want, what coordinate system, what you want to do, your physics, the laws of physics, inherent law of physics, the eventual outcome that you will get, that's not going to get affected by this. So that's the gauge freedom for any theory, independent of whatever complicated Lagrangians you will see across your careers. When you'll going and when you listen some research level lectures, I'm not expert in the high energy physics though, but you find out this Lagrangians written and you will find it, oh, what sense can I make out of it. So sometimes it do take a little bit time, but these are the easy questions that you can easily ask. Okay, oh, if this is Lagrangian, can I think about whether this is gauge invariant or not? This is the first test I'll do if I want to check whether a given Lagrangian is valid or not, or something about it. Okay, that's the approach which I just want to pass in case for at least for the undergrad students here. Now, someone will say, oh, okay, I'm not talking about the violation, but I am talking about, are these the all symmetries? Are the all symmetries either the global symmetries or the local symmetries? No, there is, universe is mysterious, and that's why I'm saying we don't know, there might be some local symmetries, means there can be more symmetries. But I want to talk about a very interesting symmetry, and which is very fascinating in the nature, which even the UG students can easily appreciate. These symmetries are something called hidden symmetries in nature. One of the hidden symmetry which I'll tell you, and I hope each one of you will understand it very easily. Now, I am telling you, think about this. This is a pendulum which is oscillating. Okay, consider it to be a pendulum. Now, when it is oscillating, each one of us know that the energy of this particular oscillation is conserved. Energy is conserved here. Now, there is one more interesting feature in it. Though energy is conserved here, 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 and everywhere, along with that, there is one additional symmetry which is going on. That is the conversion of the energy. Means here at this point, there is going to be potential energy and kinetic energy. Energy will remain constant. That's the conservation of principle. That's a global symmetry. But along with that, this particular motion is having a symmetry through which the potential energy and kinetic energy, they are making a trade-off continuously. And that trade-off is very uniform in the nature. That's why this motion is the periodic motion. That trade-off is also an additional symmetry in the system, which is making this particular periodic periodic or any cyclic motion to take place. So these kind of symmetries which we generally don't generate from, and which just generally don't give any conservation principle or so, but these are very much embedded in the theories. And this particular symmetry, we call it the energy exchange symmetry. Another, means though it might seem very trivial, but another very interesting symmetry which we do see is in the if you write down a Lagrangian for a any potential 1 by r kind of potential, any 1 by r. So 1 by r potential, you see for the gravitational force, the potential is going to be 1 by r. Then minus 1 by r obviously means minus is embedded in your Lagrangian. Even again, when you write down your Lagrangian for the hydrogen atom, then again it's going to be your Coulombic force. The Coulombic potential is also going to be 1 by r. So means both your Coulombic potential or your gravitational potential, both are 1 by r kind of potential. Now, in both of these potential, if you write down a Lagrangian, we come across, I can't show you the derivation, but it's a very beautiful derivation, and I'll appreciate in case those of you will be might haven't done it, you do it, this whole calculation for the, I have done it, means it 2-3 pages long, means for me, I have to do it from scratch though. So we figure out a very interesting quantity. That is additional hidden symmetry apart from the energy, momentum, and angular momentum conservation. That's there. But apart from there, we find out this extra conserved vector. When you have this A, like this A quantity, so we call this the Rungelen's vector, RLV vector or Rungelen's vector, whatever you want to call. This vector is going to be there. If you go to this diagram, this is nothing but you'll see this is P cross L. P cross L, P is going to be your angular momentum, L is going to be your, P is going to be momentum depending on the velocity in which a particular planet is moving. This is nothing but the Keplerian trajectory or Keplerian motion of a planet. Think about it, planet motion on an elliptical path. Okay, so on this, P cross L is going to be perpendicular. MKR, because MK is constant, R is going to be radial vector. that is going to be radially outward, and their vector sum is always going to be a vector called A. If you look on this diagram here, this vector, this quantity, this vector always remain in the same direction. When a planet do move around a particular star, then in our, at least in the Keplerian system, where the potential is going to be 1 by r, then this vector A is always going to be constant. Now, this is a hidden symmetry. It's not leading to any conserved law or conserved quantity per se, but this hidden symmetry is forcing our system or this particular elliptical motion to remain in the same orientation. It do try to fix the eccentricity of the system. That's why you don't see the planets you don't see the this twisting or some sort of motion, perihelion motion. See, so I'll just give you the means. Those of you who have studied GR, you must have studied the perihelion motion of the Mercury. So that is eventually a little bit deviation from 1 by r potential. So GR made it condition that the 1 by r potential get a little bit perturbation, due to which the trajectory of the Mercury do get this perihelion motion. Eventually that lead that this particular quantity, Runge length conservation, which is a hidden quantity, that's also get perturbed, and due to which this perihelion motion is slightly deviation from its circular trajectory do occur. So one can try to do it. Similarly, I haven't done it, the second part which I'm telling you. If you do it for the hydrogen atom, if you'll see different states, there are going to be N, L, M, there are going to be different principal quantum numbers, then there are going to be orbital azimuthal quantum numbers, NL and SM corresponding to that. Now, your 2s and 2p, they do have the same energy. That particular consequence is due to this particular symmetry only, this hidden symmetry, which forces that 2s2 and 2p to have the same energy. Even then we have the different px, py, pz, they are in the same. So this somehow this particular oscillation, though when you talk about the px orbital, py orbital, pz orbital, all these orbitals having different shapes, they are having different construction in the hydrogen atom, if you go, but eventually they do have the same energy. This particular symmetry causes them to have the same energy. Okay, I can try to do give you some calculation on the second part, but the first one is very easy when you try to solve it. So I'll appreciate even the undergrad students can try and do, because everyone do talk about the central force motion in their first years or second years. Okay, so you can figure it out. Now, this is about the hidden symmetry. They can be, means when I'm saying this, there can be many more symmetries. I'm not stopping here. I'm leaving you the space open for many more hidden or any sort of symmetries one can explore. But someone asked me this question in the very beginning, that is there some signal for the violation of time translational symmetry? So that's what we are going to talk about. And we are going to talk about the whole idea which I left in the beginning when I was saying, oh, Noether sold something for Einstein and for the Hilbert to think about. I'm going to get that particular point. I feel now we are equipped to go about and talk about that. Okay, so it's going to be very few slides. So now those of you it's a long session, so one can
actually all of them are enjoying very much, and they have asked few questions. So once you complete that, we will quickly answer the questions. It is a very intensive and amazing discussion. I can tell you this one. This is an amazing discussion. Your passion, etc., all of them are speaking. And Jim, one of my very old friend, is telling, please invite Dr. Akshay Rana back to your channel. He speaks like a Nobel Prize laureate. You can see he's from Jim, I think he's from USA or England. I really don't know, but he has been a very old subscriber and a very supportive person in thank you, Jim. That's a huge compliment. Yes, sir. You can go ahead. We have to complete it.
Okay. So now what I want to do, I want to talk about this very interesting stuff, like which I am going to call, or which Einstein and the Hilbert, they developed the theory. After developing the general theory of relativity, they were sitting with the theory and they were doubting whether their theory is right or wrong. And they call it they call it, or we call it, I don't know exactly, but this particular thing, we call it, like I'm calling it the energy crisis of general relativity. So what is the energy crisis of general relativity? And I hope each one of you can ask. So from the very beginning, or from the 6th, 7th or 8th class, when we start studying physics, we get to know about one single statement. And I hope if you are in physics or you are in any other subject, or you haven't even done science, then you can know one statement, that energy cannot be created nor it can be destroyed. It can only be transformed from one state to another state. So the moment if you believe religiously in this statement, then you will also believe that if it is the case, then it means the total energy of the universe should also be conserved. Means, should I be talking only about the only earth, the energy on the earth is going to be conserved, or it's going to be on the galaxy, or it's going to be in our observable universe? So it should be global. There should be a constant energy for the whole universe. That was the same thought that Einstein was having when he was developing his general theory of relativity. So I'll just give you a brief overview, very quick overview, how the mathematical construction of general theory of relativity was happening. So independent of any theory. So what if, even if without showing you the slide, how will I go about any theory I want to develop by using Lagrangian approach? Firstly, I'm going to write down an action. That action is going to be dependent on Lagrangian, and that Lagrangian is going to carry all the information that I want to put in the system. What was the general theory of relativity? General theory of relativity was an alternative of our traditional Newtonian force, which Newtonian force we are considering that this is based on the concept of force, but in general theory of relativity we give it a feature that everything, the gravity is a consequence of the curvature, space-time curvature or space-time, and there are particles, matter, which is going to interact. So general theory of relativity is nothing but a communication between the matter present in the space-time, and how do they communicate with each other, that give rise to something called the gravity. That's the whole picture with which the Einstein started developing theory, and he wrote down a Lagrangian. So Lagrangian, some of you might not be, if you are in UG, you might not be appreciate, but I just want to show you with this particular clarity. You have a look on this section. This section is known as the Einstein Hilbert action, and the first term of this Einstein Hilbert action is going to carry information about the curvature through this parameter called R, which is the Ricci scalar, and it relate with something called the Ricci tensors, and something called Christoffel symbols, and a lot of stuff which is valid in GR. And on the second term in this, it's going to be all the matter content, L matter. So all the matter content that's present in the universe. When you have this action, again, same principle of invariance, the same action principle of invariance will vary. The trajectory is going to be where the action is going to be extremum. You choose it, and you end up with this particular famous equation. I hope each one of you must have, even haven't understood it, you must have seen this equation, famous Einstein field equation. Left hand side talks about the take care of the curvature. Right hand side take care of the T mu means it's going to take care of all the matter content, and this T mu we call it something called the energy momentum tensor. Now, the moment you develop this theory, this theory was for any curvature. You can study, if you put in this particular T mu or the curvature, if you put a short-sided matrix, if you to choose a component, something called metric. Metric is a property of the space-time which defines how the system, how the time and the space is correlated. The correlation is given by something called metric in the tensor notion. If you choose whatever metric tensor you will put in this equation, you can get the physics about it. So when people start thinking about the universe, the one basic assumption that we made is that we consider our universe to be something called it's supposed to have the universe is supposed to have something called homogeneity and isotropicity. We consider that our universe is homogeneous and isotropic, means you go to any position, that's going to be same. You look in any direction, it's going to be same. That's one condition. And second, we were having the observational signature that our universe is going to be expanding. So when we are going to write down a metric or a metric for homogeneous, isotropic, expanding universe, for that we write down this metric called ds square in this form, minus dt square plus at. So here this at parameter is known as something called the scale factor parameter. So this do take care of the rate with which the universe or the space is expanding, because if we are talking about expansion, we are talking about how the universe is expanding. The interesting thing about this theory is that if I take the time derivative of this g mu nu, then it's not zero. time derivative of this space time is not 0. What is it telling you? Means if I make a transformation if I make a time translational transformation, if I make a transformation from t to t prime plus delta, then the way we were having in the pendulum, when I made a transformation t to t prime plus some epsilon, then I was able to see that my action was constant. But I can't show the mathematical steps here, one can try to do it. But if you do the same exercise in this particular action for the general theory of relativity, we figured out this action is changing. And it put a lot of kind of the question on the validity of general theory of relativity. How come something so fundamental which we do everywhere in the nature, that the action, Einstein Hilbert action under the time translational symmetry is not invariant? And because Noether's theorem was, Noether came later, but because we were thinking about it, so it put a question whether are we saying that the total energy of the universe is not conserved. Your total energy of the universe, you cannot put a constant number. No single, the red term, you can, no single global energy number exists. So there is no total energy of the universe. Oh, you can say, oh, the total energy of universe is that joule, or means any number, means in the terms of unit. You cannot put a number to the total energy. But if you do a little bit calculation, and if we try to study about this energy momentum tensor, let me just tell you briefly about this energy momentum tensor. It's a second order tensor. So any second order tensor with the four vector component will be having size 4x4. This term T00, this T00 here is carrying the energy density. All these diagonal or terms like T01, T02, all these carry the information about the momentum. And if you are making a translational, means a time translational, there is no conservation. But if you are making a local transformation, a positional transformation, where you are going to have one position to another position, then we figured out that we do have a local conservational law, which is given by del mu t mu equal to 0. So this is valid, because remember, I am talking about this del. I'm talking about this del is nothing. This is a covariant derivative in the sense that it is going to have local partial derivative plus some additional. Have a look on this. You have this additional term, which are these symbol like delta. We call them the Christoffel symbols. The one Dr. Shonak was a while ago talking about when he was explaining, trying to tell you about the parallel transport. So means if you want to take a derivative with respect to t mu, you have to make these corrections in the space-time of these Christoffel symbols. And those of you might have taken a course on GR, you must have seen that in any local frame, if you write down a Ricci tensor, that's going to be, the rate of change of Ricci tensor is going to be constant. It's going to be 0. Ricci tensor is going to be in the local frame is going to be 0, which take care of all the space-time. So it put Einstein and Hilbert in a very, means one can try to solve this. I am not going into the mathematical calculation of GR, but I just want to show you this equation. This is known as nothing but the conservation equation. The way you have del J by del T plus rho V in the electromagnetic theory, in your quantum field theory, you have the conservation equation. Similarly, in the GR, in the tensor notation, this is going to be our conservational law. But this conservation law is valid for the local transformation. So it was putting Einstein and the Hilbert in a very tight patch. What they are trying to say, or what their theory was trying to say, was that, oh, you don't have a global time translational symmetry. That's why the whole universe cannot have a global energy, cannot have a constant energy. But when you are making the local transformation, local symmetric transformation, then you are finding out this local energy conservation. So in the local space, wherever you go, you choose any local space, you will find out energy conservation. But globally, you talk about the universe, then you don't see a constant static number or constant energy number for this. And now, because by default, Einstein has developed the special theory of relativity. Before that, we have done the whole Newtonian mechanics and everything. Everywhere, energy conservation was so fundamental. So even for the calculation, when they, before turning to the Noether or some to other alternative, Einstein tried to modify his theory as well. He start putting this additional. So along with the team, he start putting this additional tensor, which he called the some pseudo tensor. taking some motivation from the pseudo forces or something. But even whenever he's putting, these were just like some coordinate change when you are making. This transformation was not leading to some physical significant quantity. You are just making some corrections which are going away if you are making some coordinate transformation from point A to point one system to another system. So eventually the first thought that came to both mind and that maybe either their theory is missing something, or some symmetry is broken. Symmetry is broken means the system is making some choice when they are writing this equation, and they work for figuring out why they don't have this particular calculation. And that's when, with this problem, Hilbert contacted Noether, called her from Erlangen called him to University of Gottingen, where, as Dr. Shonak also pointed out, she started teaching under the name of David Hilbert, and she was also given a post which I heard, maybe one can check, unofficial associate professor or something. Okay, so that's means, and at that time talking about up to 1922. She gave this in 1915 after the General Theory of Relativity. In 1919 she published the paper, but even after that, for around 5-7 years, Noether was teaching as a unofficial professor. Later she get some permanent position after 1992, but that's the irony in that some sense. But what Noether came, and what is the contribution of Noether when she came? She did a very interesting stuff, and maybe this mathematics might not be very clear immediately. What she did, let's do, when you are not able to prove, it's a general intuition in physics. When you are not able to prove something, what she forced in this equation, she said that let me force a time symmetry. She put something called killing vector. So in the general theory of relativity, we have these vectors which we call the killing vector. So they are not the vector to kill someone. They are just some based on some scientist. I'm missing the first name, but there is some person, some ABC killing a general relativist person most probably. So on the name of we have some these vectors. When you multiply these vectors with a particular quantity, you put them together with a either with a Lagrangian or with respect to any metric. You put them to force any metric or any Lagrangian to be constant in any given direction. So in some sense, let me put it in this way, that she forced time symmetry in the Einstein Hilbert action through this particular vector, which is k nu, which is time-like vector, which she chooses. Time-like is going to be nothing but 1 0 0 0. So it's a time-like killing vector going to be. If you do the complete math, then it will be making sense. By force, if she put the time-like symmetry in the general theory of relativity, she was able to show that the energy is conserved. And what she made a statement out of this, she said that to Einstein and to Hilbert, that our general theory, or the theory that you have developed, it is not missing something. It's not broken. Symmetry is not broken. It is a theory which naturally don't have a time translational symmetry. And because it doesn't have a time translational symmetry, that's why the energy is not conserved. And that's why when you talk about the expanding universe and the complete universe, it's a very absurd question to ask under the GR, at least I'll say, that what is the total energy of the universe? Sometimes I used to ask this question, and I used to get this question as well, means both way. People do ask, where the universe is expanding into, where the space-time is expanding into. What is it getting generated? From where this additional energy is coming? If the energy is constant, how this energy is getting distributed? So all these questions are very much answered by the general theory of relativity, because there is no symmetry, time translational symmetry. So giving a number to the total energy of the universe will not make any sense. And that's how, when we say about, and that's how that Einstein and Hilbert get convinced, okay, this is going to be our general theory of relativity, which is not time invariant, which is going to have local symmetry. In local space time there is going to be energy conservation, but as a universe as a whole, there is not going to be any global energy conservation principle. And that's what
just to tell you that, sir, when you are talking about killing, it is basically Wilhelm Carl Joseph Killing, He was a
Okay.
German mathematician who made important contributions to Lie algebras and non-Euclidean geometry. He actually invented what is called the killing vector.
Killing vector. So even the means like point. So this LK that you'll say means I'm just telling you the name how the whole dynamics works. So that's a thing to be calculated and done. It's a rigorous stuff to do and to calculate. But these are known as the Lie derivative. So this del mu k nu, this is known as the Lie derivative for this Lie or for these killing vectors. So now that's the answer to the person who asked me, can the time translational symmetry be broken? In local universe, it can't. Energy is conserved for us. You go to galaxy level, galaxy cluster level, you go to observational universe level, the whole observational universe you take as a system, this is going to be conserved. But the moment you will talk about the complete universe, then time translational symmetry doesn't hold. That's why the total energy, you cannot have a no global number for it. Okay. So with this, I'm trying to conclude here. Now there are means when I was exploring and I was thinking, still it's a lot of time I have to spend. There are many terms which will come across. I haven't talked much about something called supersymmetry. That you will, because that seems like, if you are talking about symmetry, why we are not talking about something called supersymmetry? Why we are not talking about something called symmetry breaking? I haven't talked in detail much about the Lorentz boost or Lorentz invariance and transformation. All those topics, there's a lot more one can explore this particular topic, but I would like to conclude here for today. And that's all from my side on this topic. Thank you very much, sir.
Thank you very much, Dr. Rana. It is almost a complete detailed class that you have taken, not a podcast. We started with building up the basics of symmetry, violation, and then we moved into Noether's theorem, completing Einstein Hilbert action. To be very honest, Einstein Hilbert action is one of my favorite topic, where actually this GR principle is based on a global nature, not on the local nature. Quickly, sir, we are almost almost 2.5 hours. Quickly, if you can answer this question. First of all, a great appreciation coming from Rana Singh. Dr. Akshay Rana speaks with such brilliance. Love how he weaves together numerical equations with interesting stories. Motivated to read further about Noether's theorem. Wonderful session. So thank you, Rana, for putting up such compliment. I think, sir, you can see now the things on the screen, which it is visible.
Yes, it's visible.
Okay. Prakash Tare is telling, thank you very much. Okay, I will just take quick questions. First of all, Shubham Rana is telling interactive, this is an informative interaction. Okay, a question from Ayush Bhattacharya is that, sir, is this Lagrangian density or Lagrangian because inside integral it is D4?
Okay. So you will call it the Lagrange density in that sense. Yes. That's fine, because you are saying action when you are writing integration L4x. Yeah, that's correct.
Okay, Jim is telling, please invite Dr. Akshay Rana back to your channel. He speaks like a Nobel Prize laureate. Okay.
Thank you very much.
Next question from Sanket is that, does this conserved quantities coordinate independent like coordinate system independent?
Yeah, I mean, like when you are talking about conserved quantities, they are independent of anything. Independent of coordinate, that's the least one can expect from these quantities. Means if you are changing a coordinate from, either you go from Cartesian to spherical or any sort of coordinate transformation, you go from one inertial frame to another inertial frame. So all these quantities, all these symmetries are supposed to be, they should be conserved. That's the, whenever someone go and develop a new theory, that's the first thing to test, whether all these conservation principles are holding under different
holding or not. Right, absolutely. Sir, Gurnoor Singh is asking, sir, if the universe were only homogeneous but not isotropic, would the laws of physics, example Einstein's equation, still allow an expanding universe model? Explain what kind of symmetry would remain.
So it's saying, sir, if the universe were only homogeneous, okay, only homogeneous but not isotropic. See, again, means symmetry is going to be there. I mean, only homogeneous means you are saying, so how would you make it? when you are going to write down your G mu, means if you are familiar with the metric tensor, then you are going to put your so much. See, but no, but if you are going to have a homogeneous space-time, it's going to be isotropic. So I should no, I should not say this, because if the system is isotropic, then it's homogeneous. I was thinking if it is isotropic, it's always going to be homogeneous, but vice versa is not true. So obviously, means one can try. We'll see. Then you will write down your G mu. So if for making that, you are saying that your R part, means because in the space part, your R part is going to have the symmetry, but theta and phi can have different kind of composition in that manner. So there can be symmetry. What kind of symmetry one can explore? Means I don't know right now actually what answer I can give to this, what exact symmetry will occur, but that would be interesting stuff, I think, because see, every time we write down a new theory, there are going to be this means especially at least in the GR, when you write down any, let's say I'm talking about a inhomogeneous universe. Okay, when you consider your universe to be even the not homogeneous and isotropic, completely inhomogeneous universe, even then there are going to be something called this Bianchi identities, which are the combination of different quantities. So over there, your conservation principle is not going to be traditional del mu t mu, means the one we were having. Those form will change, and now it would be difficult to pinpoint what exact symmetry will be there, because the kind of perturbation, the kind of change that you will make your theory, accordingly it will change. So giving a name to that, I'm maybe someone expert in the field might give a answer to this, but maybe Dr. Shaunak can tell you much better about it. But I can't name any symmetry per se, but yeah, they're going to be conservation.
This is a hypothetical case, so we have to take a lot of mathematics and then we can think of the symmetry. It just cannot come out like this, right? Ayush Bhattacharya is asking, sir, is it necessary to complete classical field theory before quantum field theory?
I think yes. Even if not completely, at least if you have the good understanding of the Lagrangian dynamics and basic classical field dynamics, that's required. That's very much required. Okay, because the moment you go into, and then again with the quantum field theory you are talking about, then you have to have good knowledge of tensors, not only the classical field theory, because everything you have to write down in the form of tensors. So so that way you have to have good knowledge of special theory of relativity, some basic understanding of, means not very detailed in per se that I'll say, but understanding of quantum mechanics as well, and the classical dynamics is must. So these three, so eventually quantum field theory, you are merging special theory of relativity with the quantum mechanics, and that's how you are developing. So these are basic ingredients.
Absolutely. Ayush, I would request that I have very detailed videos along with book recommendation, mathematical prerequisites on how to learn quantum field theory on this channel. You can go ahead and understand. It is a very detailed video, step by step, everything I have given to understand from quantum mechanics, how to move. And as Dr. Rana told, yes, you need to have special relativity, classical mechanics, and basic non-relativistic quantum mechanics also, because without that, so that is why it requires a lot of mathematics to know. Okay, thank you so much, sir. Manoj Kumar is also telling thank you. Anurag saying good session indeed, sir. Hats off from Stephens. And I don't think we have any further question except one. This is done. Okay, and my last question is that how to understand that which interaction to put in which group?
Which interaction to put in which? Oh, okay. So that's interesting. So you are talking about the continuous symmetry, like when we do the local symmetric transformation. So it is very much because we don't have too many interactions. So luckily we do have only 4 interactions. You have either gravity and you have EM. So both of those will go into U1. U1 means that because they are going to be U1 groups, because they are going to have the dimension to be unitary. And then when you are going to have your weak interaction, that will going to be twofold. So in the sense it will go into SU2. Then your strong one will go into SU3. So we do have limited choices in that case. So means
right.
By theory it will come, but anyhow by intuition one can figure it out. So by mathematics that will eventually turn up that what kind of field is causing what kind of distribution in quantum field theory, whether it's electric field or whether it's weak field or whatever. So or if you develop any other theory per se, then there could be different scalar fields as well. So that way you have to figure out.
Okay, Ayush Bhattacharya is telling that as a physics undergrad and enthusiast, I really enjoyed this session. And I will take the last question from Anurag. What tells us that we can achieve a composite Lagrangian for all the forces? We have achieved unification in 3 of the forces, but gravity remains. Yeah, I think that is a very pertinent question. That is what all the theorists are now willing to achieve, a theory of everything.
That's I'll say it's ego of theoretical physicist. If we can merge 3, we'll merge 4. Why not? So that's the effort going on again. Yeah, the whole.
Yeah. So it was in an interesting lecture again coming up from Subhash Chandra. So I mean to say, I really don't have any words to thank you, sir. It is amazing session, 2.5 hours with all your beautiful knowledge in terms. You actually, I think this will come as a knowledgeable video. So anybody who is willing to learn about symmetry in future, because it will remain in YouTube, and I think that it will come as a wonderful lecture. So thank you very much, sir. I really have no words to tell you. A lot of people are telling, Ayush is telling, I'm really grateful to you both, sir. Subhash Chandra is telling it was a very interesting lecture. Sir, really thank you, and thanks for all the viewers for asking very intelligent questions. And that's all. So we will sign up, but sir, just stay on the line for 2 minutes. Okay, Ayush is asking, is it possible, sir, to contact you for project? I think I will put up sir's email ID over in this job in the description box, and later you can write to him. Although he's a very busy person, I think he will answer to the queries. Sir, just stay for 2 minutes, and with that, let me thank Dr. Akshay Rana for a very detailed and a lengthy and a beautiful, amazing podcast. And thank you for all the subscribers for asking these beautiful questions. And most importantly, all of them, sir, you have not been seeing because I'm in the back end. All of them since the beginning, they are all online. Not a single person have left the podcast, which is almost 2 hours, 30 minutes plus. So this is really interesting, and it speaks that how well you speak. And thank you very much for that. So we will be again back for Physics for Students next month with some interesting podcast, this stuff coming up on astrophysics. So please stay tuned, and a lot of heartfelt thanks to Dr. Akshay Rana. So just stay for 2 minutes. I will just have a word with you. Thank you very much.
Thank you very much, sir. Thank you, everyone.